Welcome to the AI Engineers World Fair. This is the first workshop. There's a few other running, but thanks for coming. We just arrived from Australia with my brother. I think he's over there somewhere. But yes, we just came here. Yes, we didn't know a lot of stuff about SF, and I think maybe the US is a bit different from Australia. But yeah, we're very excited to be here. So we're gonna stay here for a few months. So if you want to meet up, you can just hit me up, email or Twitter or wherever. So today I'm going to be talking about low-level technicals of language models. Yes, I'm Daniel. So we do have a website called unsloth.ai if you want to look that up. There's cute sloths and stuff. So my brother designed that. We'll be using two tiny URLs. Oh, did it? Okay, it's still working. Yeah, so we'll be using two tiny URLs now. So the first one is, oh wait, I'll show. Yeah. So the slides are at tinyurl.com/unsloth. Hopefully that works. And there's also Q&A, so I'll be monitoring Q&A. You can type any question that you like. And I will be answering questions as we go. And that is at tinyurl.com/unslothqa. So if those two work, so there'll be on the bottom, if anyone doesn't get this, there's on the very bottom of the footer, there'll be we'll re-show these links. Okay, does it work? Yes? Okay, good. Okay. Yeah, so you might know me from my tweets. So Gemma released an open source model a few months ago, and we just found a few issues and bugs through different implementations. So for example, the first tweet that we ever did was about some sort of the approximate GELU bug issue. And so multiple implementations of Gemma that had different implementations. Some of them use exact GELU, some of them use approximate. And so which one is correct? And so that's the question. And so we just tweeted about this. And that was our first issue that we found. We thought this was just one issue, but actually there were many issues. And so we found more bugs. And so I'm assuming maybe you know me from this. We did get partially recognizable through our Gemma bug fixes. So yeah, so today we'll be showing you how you can actually find these bugs and issues in language models, and how you can actually analyze and do this yourself without us just doing it manually ourselves. And hopefully this can be an open source project where everyone can find these issues automatically and help us to solve these issues. I always thought about can we automate this? I don't think so it can be automated. There are actually many issues with these implementations, and it's not just Gemma. For example, we also analyzed Grok, and there's some weird things in their code, they're scaled by 30 times 10 x over 30. It's just a clamping mechanism. But you can see I also make mistakes sometimes. I said it's division and not multiplication, so sometimes I misread the code. That's because I spend when the code gets released, I quickly try to analyze them, and sometimes I mistakenly say stuff. So I have to lodge showcase corrections. So yes, I am still human. But yes, we analyze lots of models and stuff like this, and hopefully by the end of these workshops, well, actually it's actually not one workshop, it's going to be multiple things in one. So I decided to talk about 3 things, but I'll tell you about that later. Hopefully you guys can analyze and learn about how to do find bugs and stuff like that by the end of today. So another one I did recently was NVIDIA's Nematron. I don't know if you saw this, but NVIDIA released a 340 billion parameter model, which is extremely large. I'm assuming this is in in preparation. They have to release this earlier before Llama 405 billion, right? So they have to do this quickly. But there are some weird, interesting things, they use the squared value and not the normal swigglue and the other types. So that was very interesting. They were actually the first, well, actually not the first, but the first big model trained to be using these new, other activation functions. And there's other weird quirks and stuff like that. And hopefully you'll be also able to analyze, whenever the code comes out, just read it and you'll get it. It does take some practice. Okay, I take okay, the first time when I read this code, it took me many days to read through all these architectures and understand exactly what they are. But now it takes 10 minutes. So I'm sure you can just the code comes and just read it. That's the whole goal of today. And also, language models, if you don't know, they're not just like issues and bugs and analysis of these architectures. The tokenizer is a totally separate beast from language models, right? Tokenization is like extremely annoying. So like, I also tweeted about like, there's like different types of tokenization issues, like Mistral, Llama, Mixtral, like all these different types of like variants of Mistral from the Mistral team. They have like different tokenizations if you didn't notice. Like so the smiley face, the sun smiley face is a space. And if you actually tokenize them, depending on the model, you have different results. And the question is, which one is correct? Unfortunately, I do not know. I did ask the Hockey Face team for this, and according to them, some of them are correct, and some of them are just because the Mistral team forgot to update the model to the fast tokenization variant. We will be talking about this later as well. But you can see, even before you can train or run the model, the tokenizer is broken. So what are you going to do? It's a multi-pronged problem. So we don't just do language models. Like we don't, our experience is, a bit broader than that. So we actually, like, I used to actually major in maths and computer science. So yes, very fun. Well, actually, I kind of did very badly in maths. But anyways, yes, very, very fun. So like SVD, I don't know if has anyone done normal machine learning here? Oh yes, very good. There is a few people. So like the SVD, I'm assuming like most people know PCA. Yes, principal component analysis. Yes, okay, very good. Data visualization. It's a very powerful technique. More people should know about it. SVD, okay, I don't know if people know about SVD or like, okay, yes, it's a bit less well known. I'm actually a bit confused why people don't know SVD. It's actually the algorithm that's one of the most important algorithms in all of like maths and computer science. It literally underpins like many applications, and it is extremely important. Maybe we'll talk about that, but yes. I'm a huge proponent of like telling people to learn more about SVD, so please do the singular value decomposition. That's like the must. Okay, like that's the most important algorithm. It's because it's like one algorithm, it can like spawn many other algorithms, and it's like can be used for many purposes. There's also like the QR decomposition. Okay, probably don't, no one knows. The LU, Choletsky, like there's a lot. Randomized SVD, yes, that's extremely important as well. And yeah, so we don't just do language models. You can ask me any questions about, stuff, maths or computer science. You have a question? Or?
Real quick, so do you think, so for the Nemotron 340B, is it a unique architecture because you can only use Nemo loader right now to load and train, and, do the, I think the data system is the most valuable part, but we are attempting to try to convert it to a Hugging Face transformer safe tensors. So, but we've had issues because we don't have the modeling file. So I was wondering, do you think that it's similar to, so at the same day, they uploaded a 70B of Llama 3 that's Nemotron as well. Do you think that we can get some clues to how to build a Hugging Face implementation of the, from there?
So the question was, for Nemotron, the code was not released for the actual inference and mod training. You have to go through the Nemo training framework from NVIDIA.
Well, what I mean is that I can dump the weights.
Yes, but the code, yeah. I was actually planning on doing something like that, but as you know, we didn't have time to do that, so I would probably, I might take a crack at that.
Also, is there going to be a Q&A? I don't want to ask any more questions.
Oh yes, no, there is. So you can log questions on Q&A. There will be Q&A. So you can like, anyone can like raise their hands and like ask a question. Like I'll just repeat the question. But there is like the slider if you want to random questions. I will keep monitoring. So like, oh yes, the other one was like another paper called LoRa learns less and forgets less. It shows that fine-tuning via LoRa does not really work for learning new knowledge. And well, it depends. Like it depends on how you actually read the paper. Like some components were incorrect. They didn't actually train on all linear layers. They kind of forgot a few. And you need to do some sort of like special parameters to make this work. And we will also be talking about that as well. But I was just trying to show you that, we don't just do language models. So we have like a whole wealth of knowledge across different industries and stuff. Well, not industries, topics. And you can ask me any question that you like. So Unsloth, yes, we launched this last December. So I launched this with my brother. It's a bit outdated, the stars, but anyways, I think we have 11.9 something K or something. I don't even know now. But anyways, we launched this last December. It generally makes fine-tuning of language models like Llama, Mistral, Gemma faster to 2 times faster, generally speaking. And with like 80% less memory usage now, we have like some new methodologies which reduce memory even further. And the trick is there is no degradation and accuracy. So like, we don't do any like approximations. That's the whole purpose of doing the optimizations is we don't want to lose any accuracy. And so we do like Triton kernels. So this is like from OpenAI. It's a language to do like CUDA programming. Essentially, it's like an intermediary between the CUDA code and Python itself. And we'll be showing some Triton code. I don't know if we have time for like programming Triton, but that'll be another topic. And yeah, so like the whole purpose of Unsloth is to make everyone be able to fine-tune their language models with very bad GPUs, right? So like Tesla T4s, the free Google. Does anyone, like people do know that Google Colab has free Tesla T4s, right? Yes, yes, right? 65 teraflops, right? It's actually not that bad if you use it properly. Just a reminder, there is a common misconception that the P100s on Kaggle is faster. That's actually not correct. P100s, I think, are 5 times slower than Tesla T4s. So although it's actually more expensive as a GPU, I think, but it's actually slower for, so please do not select the P100s on Kaggle, right? So Kaggle has 30 hours for free per week GPUs, and you get 2 Tesla T4s. So that's 130 teraflops per week, 30 hours, and that is actually very powerful. I think that's the same as RTX 3070, although I can't remember exactly, but yeah, so Kaggle has 30 hours for free per week. Google Colab, it depends on how much you use. Normally, you get 4 hours per day, I think. I guess the Pro is not that bad. It's like $10 per month. You can actually get, like, yeah, it's pretty good. Yeah, so probably get Pro. I do not suggest, I mean, you could use like RunPod and Lambda Labs and stuff like that. I guess that's another option. But we do actually share a pricing comparison. So what you need to like be careful when you use GPUs, there is a big issue is like, oh, look, this is the most, I want to use a H100. Did you actually check how much flops the H100 provides? Be careful of NVIDIA's marketing. It's ×2 because it has sparsity. So just be careful of that. And also, you have to be careful of the flops when it's like float 8 or float 16. So just be careful of those. I do have a pricing comparison where we like normalize by like the flops with no sparsity. And we'd like look through like Lambda Labs, RunPod, Google Colab, AWS, Google Cloud. And I think RunPod is mostly pretty good. Yes, question. Oh, the sparsity? So, okay, so the question was, why is ×2 for flops for the sparsity feature in NVIDIA GPUs? So sparsity, the sparsity feature, what it does is you take 50% of the weights and make them go to 0. And NVIDIA essentially allows you to train this 2 times faster by not doing matrix multiplications on the zeros, right? So you're like, 2 times 0 is just 0. So like you essentially don't fire the transistors. And essentially this makes it 2 times faster. Well, that's actually not, that's just a higher level overview. But like essentially you like compress the matrix into this special format. And then this NVIDIA special format allows you to do matrix multiplications 2 times faster. Yeah, so it's sparsity. Does that? So it's on H100s, it's on A100s as well. So your RTX 3060, your RTX 30 series has that feature from RTX 30, the 30 series. I think it has, yes, I think it does. So if you want to enable it, the biggest issue is that the language models, most companies do not train their language models with sparsity enabled. If you set this like weights go to 0, you will actually ruin the behavior of the model. So there are like papers which show that you can actually do like turn on the feature and then you can do fine tuning to make it work. So there are actually papers which do that. So in theory, you could enable this, but it depends on like what models are released from the large companies. Yeah, I'm assuming, I think I do know if Facebook is like, they did implement sparsity in the Pytorch and Xformers library. So I'm assuming they might be focused on sparsity because you get ×2 faster. And if you know like OpenAI, like they keep saying, oh, it's 2 times faster. I wonder why. Why is it 2 times faster? Why is it the 2 times faster, right? So like, could it be sparsity? Could it be float 8? Right, float 8 is generally 2 times faster. Okay, not exactly, but like approximately 2 times faster. So all these like things when you hear 2 times faster, where does it come from? Could it be these things? although we don't know, but like we're just guessing. Yeah. Any other questions? Okay. Just remember, you can raise your hand, or you can do slide. Wait, are there any? I'm assuming there's no slider questions yet. Yeah, okay. Yeah, it's just raise your hand. So for Unsloth, we do benchmarking against Hugging Face plus Flash Attention 2. And we just show our benchmark. This is kind of old already. The memory reduction is much more now. And we do a blog. We did a blog post with them. So thanks to Hugging Face for the collaboration. And essentially, all you need to do is, from Unsloth import fast language model, and we try to make it as easy as possible for people to fine-tune a language model. And yes, we'll be talking about Unsloth a bit later. Oh, there is a question. Is it a myth or solid hypothesis that linear versus cosine, then short 1 to 2 epochs versus 3 to 5 epochs is highly generalized? I think it depends. So like for training methodologies.
Sorry. So is it a myth or solid hypothesis that linear versus cosine, then of course short epochs versus long epochs is the highly generalized best way to train any standard-based model?
I think it depends. So there are like some research papers which show that cosine or linear schedules, I mean, it depends. To tell the truth, I think it's a toss of a coin. I don't think so it's actually that important for the learning rate scheduler. I think it more depends on like the data set, the number of parameters. There are like research papers which show that if you just simply change from untied weights to tied weights, you can get like better accuracy for smaller models. So I think so the learning rate schedule is not that important. You might get accuracy plus 0.1%. Just train for more data. There we go. Right, get more data. Oh, wait, I pressed back. Just train for more data, and I'm assuming it will be similar. But to tell the truth, I think it's best to like do small experiments and then like test which schedule is the best. But I don't think so it's that important. I think for the number of epochs, that's actually important. These like big companies, to tell the truth, I'm not sure what Llama, like 15 trillion tokens, is it actually 15 trillion tokens? Or is it like 5 trillion tokens times 3 epochs? I do not know, right? These questions are very important. If it's 5 trillion tokens times 3, that's actually very different from actually 15 trillion tokens in total. But that's actually very, very different. But in general speaking, like, if you train for more epochs, 3 is generally the good, like approximate 3 epochs. 1 is actually the best for pre-training generally. You shouldn't like retrain your data like multiple times. But yeah, so did you have a follow-up question or no?
Well,
yeah.
So basically, learning rate was one of the big issues you fixed with the Gemma implementation.
Oh, yes.
So that's why that's where my pitfall was when I was training my 2B for Gemma. And so I actually trained it pre your fix, and somehow it turned out to benchmark and after your fix is better than, I don't know what happened, but it now is like one of the highest ranking benchmark 2Bs.
Oh, okay.
So I don't know, like what do you have any theories about what could happen? I trained it on the Transformers broken version, and then subsequently using axolotl and using a very hard, we brute forced a learning rate, basically. But it turned out surprisingly well, and we didn't use Unsloth, but we used like ATVUs.
So this is after the fixes that we did, like it does.
Before.
So before does better.
No, before it was usable. Everybody else was unusable, right?
Yeah.
But it was usable, which was surprised me because everybody else's was unusable. But then after your fixes, we are now the top. Well, my company has on the OpenLM leaderboard has the highest.
So you didn't even retrain. You just.
No. So after fixes, somehow
it made it better. Okay.
Do you have any theories on that?
To be honest, I do not know. I think like because the fixes that we did for Gemma are like multi-pronged. Like it's not like one fix is like 9 or something. So I don't know which fix caused the change. There could be like all of them maybe. I don't know.
It's kind of like just for me when I did the training, right, and it turned out good, and then I heard from like all my friends, oh, I can't do this. It's like it just shocked me, I guess.
Okay. Yes, that is quite shocking. If like you didn't. Yeah, we changed the code, like we kind of like fixed all the issues, and then you don't need to retrain it, and it does better. Okay, that's a very interesting phenomenon. I do not know.
I can send you the code.
Oh yeah, okay.
Open source on my.
Okay, yeah, great. Yes, to be honest, like language models, I mean, these are all active areas of research. Please, someone will do a research on that.
I'm a
Yeah.
mechanistic interpretability nerd,
Okay.
so I
Yeah.
like these like super low level stuff.
Yes. I cannot say anything other than I just read the code and fix the bugs. I do not know.
Sorry.
Yeah. Don't worry. Okay. We also like do long context fine tuning. So like we show that if you use a new methodology which does gradient checkpointing and offload it to system RAM, you can randomly increase your context size by 4. And the weird part is if you offload correctly to system RAM from the GPU, weirdly, the time of execution is just slower by 1 to 2%. Right? So like this is very weird. It's like if you can do non-blocking calls and offload the GPU like memory into system RAM, if you do it correctly, it's not slower. Some implementations, unfortunately, offload incorrectly. I don't want to name anyone, but they offload incorrectly. Sometimes they offload to disk. I don't know who came up with the idea of offloading to disk. But anyways, please try to offload to memory first and then disk. Right? Disk is extremely slow. And if you can offload to memory system RAM, you can actually get away with a lot of memory usage. Okay, so I should have put this at the first slide, but anyways, so today we'll be having 3 approximate topics. And these, I wanted to make them into like 3 different separate topics, but I guess I just mixed them together, whatever. So you'll be learning about low-level technicals of language models, for example, backpropagation. Why is transformers not O of n squared, O of n cubed for training and rather O of n squared? And there is a lot of maths, but I will try my best to reduce. I think I already tried my best to reduce the maths, but there are still some maths. So please handle the maths. I will try my best to explain as simply as possible. That's the whole goal of the workshop. So not that bad maths. You will actually understand the formulas very well. Just a reminder, I kind of nearly failed my maths in university, so do not worry. Do not be scared. It's very fine. We'll be talking about Unsloth fast fine-tuning, the best tips and tricks for fine-tuning, how do we write the fast kernels for fine-tuning, how do we actually make it 2 times faster, use 70% less memory, like how, with no accuracy degradation. And we'll be talking like some Triton, OpenAI's Triton language and stuff like that. And we'll be doing finding and fixing bugs. So this will be a constant phenomenon and theme. How do we find and fix bugs in Llama, Mistral, Gemma, Phi? We'll be talking about a mixture of experts as well a bit. Oh wait, maybe not, but it depends on time. And we'll be doing lots of bug hunting, bug fixing, and more. And everyone here will be a fantastic bug hunter and bug fixer. And we can like essentially open source our effort to fix open source models to everyone here. Oh yes, and we also have stickers. Yes, I don't know where they are, but like, oh yes, yeah, my brother has some stickers. And we bought a few of these stickers, which look pretty cute, right? So like you can, wait, my laptop has some, right? I put them on my laptop. And they're pretty cute. I really like them. So my brother has them. We'll be handing them out, as well at the end. Okay, so let us start. So the transformer, right? So like, what is the transformer? I'm assuming everyone knows what the transformer is. Does anyone not know what the transformer is? Yes or no? Like you can simply... Okay. Yes, okay. So the transformer is just an architecture that is behind all language models. So like GPT-4, GPT-3, like Llama, Mistral, Gemma, all these open source models, what are they? Like what's the architecture behind them? And all of them rely on the transformer. And the transformer is essentially a architecture which seems to be very good for sequence modeling. So it's not just for languages, it can be for any sequence modeling, right? So like if SORA is a transformer, well, not just a transformer, it's probably plus diffusion, but like it's generally a transformer. And there's other different types of models, which doesn't have to be language modeling, okay? It's just sequence modeling. And I probably show some pictures later. I probably should have explained it a bit better, but like just assume that transformers are the method behind all language models. Okay, GPT-4, GPT-3, GPT-5. Okay, I don't know if who knows what GPT-5 is, but like I'm assuming it's a transformer. The transformers just seem to be very good at learning new knowledge, injecting knowledge into the model. It seems to be very, very good at changing the weights to fit the training data, which is very interesting. And the GPT-2 architecture was actually very popular for the most a decoder style transformer. That was very, very popular. It's still used to this day. And it kind of got reincarnated by adding extra components to it. And this new architecture is called Transformer++. I don't know if people have heard of this, but Transformer++ is the GPT-2 transformer architecture plus rope embeddings, plus SWA plus RMS layer norm, and with no bias. And I think it's untied weights, although I'm not sure if GPT, I can't remember that exactly, but I think it's plus untied weights. And Transformer++ is the architecture which most people think is the best, transformer architecture for now. Yes, for now. There are probably like some other tweaks and little small things that transformers still can do, but like in general, this would be considered the best architecture. And how does the architecture look like? It is just a list of maths equations. So I just wrote down the entire transformer architecture. Well, this is Llama 2, right? So Llama's transformer architecture in one slide. And all you need to do is get some inputs, like some sort of like inputs, do some layer norm, do some rope embeddings, do some attention, plus some residual, do some layer norm, SWA whatever, residual, layer norm, and you get logits. And you essentially repeat this middle section L times or many times. And that is the transformer architecture. Okay, then maybe the math equations, I'm not sure. Does the math equation scare anyone? Or I'll be explaining each one. Okay, so like, hopefully I try to make the math equations as like reasonable as possible. In theory, if you write this down in Pytorch, oh yes, if you write this down in Pytorch, you will actually have a working implementation of a transformer architecture. And yeah, so like we'll be talking about each component separately as well. Yeah. Is anyone scared for the maths? No, yes, no, no. Okay, very good. Okay, let me just check questions. Does anyone have any questions? Okay. Okay, so did you have a question? Okay.
Well, so from my understanding, from the layer level for transformers, so it's almost comparable to cosmic Plinko in a way. Is that, I mean, of course, there's the hard math behind it. But
Cosmic, sorry, what?
Cosmic Plinko, like the drop, because there's 80 layers, right?
Mm-hmm.
In a grid, right?
So like low energy something? Sorry, I'm actually not familiar with that. You have to explain to me. What is just cosmic what? Sorry.
Cosmic Plinko.
Cosmic Plinko? Do I know that? I'm not that smart. So you'll have to like explain to me what that is. Should I search that up?
Gotcha. It's the arcade game with a bunch of pegs and you drop a ball.
Oh, that. Oh, yes. It's a Windows XP.
Output, on the bottom right.
Yes.
To visualize it, right?
Yes.
Like if you take this to visualize it.
Yes.
And then visualize the math. For example, let's take Llama 388B, right?
Mm-hmm.
It's 32 layers, right?
Mm-hmm. Yes.
And then layer 0, or I guess it doesn't matter. There's layer 0 and then layer 32, which is the output layer. Right?
Yes.
Now, when you drop a prompt into this cosmic machine,
yes,
which it's not actually cosmic, we just don't understand.
Okay, yes, it's not cosmic. Yes, it's just maths. Yeah.
But so far, it's cosmic to us.
Yes.
I don't think we understand. Personally, I don't think we understand 50% of it yet. Like
I know. I think we understand a lot, but okay. Yes. Okay. It's just maths. Yes.
You're the expert, not me. So.
Okay.
But
so you're just trying to say an analogy, like it's kind of like the game.
Yeah. So people can visualize the math versus like.
I think so.
Comparison?
Oh yeah, I'll talk about that in the slides. But like, I think it's more like, an analogy. I think it's more like you're going through like a maze. Like, okay, it's not a maze. I would say it's more like you have like every single layer has like someone trying to make you change clothes, and then each layer there's like a fashion designer trying to get you to wear different clothes. And each layer, the fashion designer doesn't like the previous fashion designer's choices, and they will change your clothes. Something like that. I think that's more like a transformer. It's like each fashion designer has like views of their own.
So it's actually quite similar, kind of.
Okay, yeah, I guess you could say it.
Plinko does have like kind of like pegs on and stuff like
Oh,
that.
yes. Wait, it is in Windows XP, right? Is it that? Am I getting confused? Windows XP, like the game? I think I played it before. Oh, okay, anyways. Okay, yeah, sorry. Yeah, question.
In the notation, is there a way to tell what's a matrix or a vector or
So when I put subscript I, it generally is, well, technically everything's a matrix, but if you see any summation signs, with subscript I, then it generally means row-wise or column-wise. The W, like if you see small, like a small W, that generally means vector. But in general, everything that's capital is a matrix. And why is it a matrix? Because it's just faster. I mean, in theory, you could convert this all to vectors, but for speed purposes, this should be matrices. Yeah. Any other questions? Okay. Next. So why did I put this? Hello, my name is Daniel. Hi, my brother's name is Michael. I hope everyone will have tons of fun. AI engineers world fairs is the best. Why did I put this? Well, does anyone notice any similarities between these sentences or differences?
Exclamation mark at the end.
Sorry?
Exclamation mark at the end.
Okay, yes, okay, except for the first sentence. Okay, anything else? Just say random stuff. Interesting, yes, okay, hello and hi are the same thing, but kind of different words. Okay, yes, yes.
Semantic embeddings. Basically, this is an example of semantic embeddings.
Okay, somewhat, okay.
Verbs are all similar. Is, will, have, they're all to be verbs.
Okay, yes, okay. Okay, well, to tell the truth, I didn't have any intention. The intention, oh, yes, go on.
I mean, it's the king plus queen.
Yes, for word to back, yeah, I know what you're talking about, yeah.
So, like, you know, it's king minus man plus woman equals queen. That's the. I think that's what you're trying to show a little. Maybe you don't have that intention, but this kind of it shows that a little bit.
Okay. Well, in theory, I guess you could have just seen the next slide. There are just 5. If you simply just look, the first one, if you consider punctuation as combined with the word, right, like hello, comma, treat that as one separate component. And if you do this, ignore all spaces. The first one has just 5 components, right? What do you think the second one? Okay, I guess you can already have the slides, but what do you think the second one has then, right? Anyone? I already wrote all the answers there. Okay, yes, I wrote all the answers, right? 6, 8, 7. Right, 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7. Right, so like if you do this, just assume all punctuation from now on is combined with the word and ignore all spaces. And this, we just invented a tokenizer. Right, so this is a very general, a random tokenizer we just invented. And each one has essentially, the reason why we want to do this is because computers they don't understand words, they only understand numbers. Right? So like you have to essentially assign each of these tokens as a number, like an ID. Right? So hello is ID 0, right? Hello, comma actually is ID 0. My is ID 1, name is ID 2, and so on. Right? So like you have to assign an ID to each of these components. If you don't do that, then a computer doesn't know what you're actually doing. Right? Computers only know numbers. So we just invented a tokenizer. I would not suggest you to use this tokenizer, but in general, it's actually not that bad. Because can anyone see any issues with this new tokenizer we just created? What are some issues? Yes?
If you include the punctuation, the tokens for Michael with and without punctuation will be different? Probably?
Yes, very good. So what do you think we should do? Okay, so the point was we included the punctuation for the words, and that is not helpful, right? So like Michael exclamation mark or Michael not exclamation mark. So what would you suggest to fix this?
I would assign tokens to the punctuation.
Interesting. So hello, and then hello will be one token, and then comma itself will be a.
Yeah.
Okay, interesting. Anyone have any other suggestions? Yes.
So the point of a tokenizer is to reduce the vocabulary, but here you haven't reduced the vocabulary, right? Because every new word will be a new token.
Yes, very good. Exactly. So do you have any suggestions for how to improve?
You could stem the word, that would reduce the vocabulary.
Oh, yes, very good. Yes, I haven't heard that in a long time. Very good. Yes, old natural language stuff. So the idea was to stem the word. So essentially you can remove like, for example, like skipping can become skip, right? So like skipped, skipping, skip, like, they're all kind of the same thing. Well, I wouldn't say the same thing, but like in theory, they're the same thing. Any other suggestions?
My with the capital M are treated differently. They mean really the same thing. So can we just lowercase them all first?
Very good idea, right? If you lowercase them all, then you can reduce a lot of issues. Is that a good idea? capital my and small my. What do you think is the difference? If you do capital my, generally means it's the start of the sentence. If you do my with no lowercase, then it means it's the middle of the sentence. So good idea though. Actually, I think so but is an old, okay, people still use but. I think there is a lowercase version of but, so they essentially lowercase everything. And I think it does okay for like semantics and stuff, but it doesn't really do well for decoder type style. So don't lowercase, but good idea. Any other suggestions? Yeah.
You build a vocabulary by starting with just the individual tokens instead of size for how large your vocabulary would be.
Yes.
And you start building word pieces from the most frequently observed.
Oh, you just said the name of the algorithm. It's called word piece or BPE tokenization. Yes, exactly. So that's actually the correct, well, I wouldn't say it's a correct way. I actually don't like that approach, but yes, it's the most recognizable and most industry standard approach is to do what you suggested, which is to start off with like small little individual characters and then combine them together based on some sort of statistic, right? You shouldn't, like, hello, like maybe hello is a word that we have to select, right? So like, but like H-E-L-L, okay, hell, okay, that might be a popular word as well in like the dictionary, but like anyways, or he, right? So he, hell, hello. Each of these might have assigned different tokens, but they might not be, right? So like it depends. And the correct industry standard is to use these methodologies to build up the component, which we won't be discussing today, but like that's for later research. Yes, okay. So let us just look at one sentence, right? The first one is, hello, my name is Daniel. Assuming our tokenization is useful, okay, let's just assume the tokenization which we created is helpful. Okay, so remember, it is just put all the punctuation together, ignore spaces, and don't do lowercase or whatever. Just tokenize it as it is. It's not very useful, but who cares? We'll just say this is a good tokenizer. The question now is, if I select the first token, hello, right? Let's assume, I don't know if, okay, the color's not very good, but like my name is Daniel is grayed out. I'm not sure if you can see that, grayed out. Pretend someone types in hello, comma, right? A language model should predict what's the next word, right? So how does it know to predict my, right? You know when you type ChatGPT, it goes from left to right. Like you type something, you type some sort of instruction, and then ChatGPT will like print the words from left to right, right? So like, why is it printing words? Can anyone tell me why is ChatGPT printing words from left to right? Why is it not doing right to left? Or why does it not just spit out everything in one go? Yes?
Because it's basically a sequence modeling, and it's just taking, for this case, hello, and then predicting what's most likely the next word, depending on the prompt you gave it. So
Exactly, correct. So because it's a transformer type, decoder type architecture, it is predicting the next word based on the previous words. So very good. And so the point is we only can have the language model see previous words, not future words, right? If you accidentally put the future data in, your accuracy might go to 100% if you use future data, so please do not do that. This is actually a very common mistake. Like, I'm not saying this jokingly. It's a very big issue in research. So please read the paper before you actually, like if you read research papers, please see how they did the methodology. Always read, always ask the question, did they put future data in when they did the training or doing the research paper? Okay, this is a pervasive problem, I'm not joking. You can see like weird accuracies, like if you see papers which have like 98% accuracy, question, okay? Or 100% accuracy, how's that even possible? How can something be 100% accurate? Question. Right, and so the most likely scenario is they use future data. Yes?
Do you find the paper itself will actually catch this? Or I feel like I often find that like the logic in the paper makes a lot of sense, but then I'm really questioning like how likely their code actually implemented what they think they are doing. Right? Like do you find it more like the paper actually gives you that issue or that the code has some bug in it?
That is a very good question. So the question was like, is it the research paper, like the methodology itself, using future data, or is it the code implementation, the problem? Now, that's actually a very good question because it depends. So I think if the researchers, I think normally in research papers, one person does the coding, Some other people do like secondary coding, and then the main researcher who makes the idea, they don't actually do the coding. So the coder might have misinterpreted the methodology. To be honest, I don't think so that's the case. I think it's actually the methodology that's the problem. I think if the researcher, like the main researcher, if they find out that their method has 90%, 98% accuracy, like why didn't they question the results? Like wouldn't that be very sketchy? Like 98% accuracy, 100% accuracy. I'm not joking, this is actually a very serious problem. So if you read enough research papers, you'll see this problem is always the same problem. It's always using future data. So yeah, I think like if you don't, yeah, okay, I won't comment on any papers. Anyways, yes. Okay, does that kind of answer your question? So it depends. I think in general, I would say it is the researcher's, the lead researcher's responsibility to correct these mistakes. Then you shouldn't be the lead researcher. So like that's my take on that. I think the coder, I mean the programmer might have some issues, but I don't know. I think I blame the lead researcher. Any other points?
Seems like you're saying the main red flag is like a huge leap in performance.
Yes. If you see huge leap in performance, question, it's probably future data. Actually, I wouldn't say it's probably, it's like 50% sure it's future data. Yes, question.
Do you think, methodology like they do like a train validation test split, and what if the way they sort of like did that, they did shuffle the data?
Oh, yes.
The tokens, like whatever we are calling future data, what if like the tokens, name entities and stuff, like they didn't actually shuffle that, right? And that was all in the training data and the test data or the validation split, whatever that just essentially have tokens that they've already seen, so it's able to do a good job and get 98%.
Exactly. So the point was, in the test and train split, sometimes, although you might not be using future data, you might like accidentally put different components in the training set from the test set. And depending on how you split the data set, you might actually mix the data sets. Is that kind of correct?
Yeah, it's like basically, are you biasing basically?
Yes. The distribution itself.
Yes.
Yes. So that is why you have to be very careful to how you split the data sets. Right? For training and testing, you have to use stratification. You have to inspect the data before you do it. You must enable random shuffling. Right? There is actually a very, very common question on Pytorch. How do you not enable random for Hugging Face? How do you not enable random shuffling for Hugging Face? They purposely disabled this. Like think about like why? Because like people might forget to randomly shuffle. And actually, this is a pervasive problem in Kaggle competitions. People like to like train on the tests. Like they give you like 20. Normally speaking, you should have 20 test, 80 train, right? So like, but people like to like the final submission, they use even the test in the submission. So, you know, it is a pervasive problem. Any other points and questions? Okay. So what is a language model? Given the word hello, can you somehow predict my name is Daniel, right? So like given the word, right? So given that token, can you predict these extra tokens? Remember, carefully, I purposefully only went from left to right, right? So like hello can only predict name, is and Daniel, right? It cannot predict, right? You can't use the word hello to predict previous words, right? That's cheating. So that is sequence modeling. And the point is, when you chain them together, let's assume that you predicted the word my as the next word, right? So now you have two pieces of information. The text that you see is hello, comma, my. Using these two pieces of information, you want to predict name is Daniel. And you keep doing this. And that is a language model, right? That is essentially a language model. What is it doing is you start from the first word, you predict the words into the future, and you keep doing this iteratively, right? And so that is what ChatGPT is doing. Does that kind of make sense? And remember, the point is never use future data. Okay, I know I keep stressing this, but like this is actually a very big issue in machine learning and AI, right? This is actually the biggest issues I find, in my opinion, is using future data. There's so many papers which do this. Yeah. So the second point is you must tokenize each component into numbers. Remember this? So I'm just going to cook up some numbers. Hello will be 0.11 minus 0.123, 102. Okay, I just made those numbers up. Daniel is 0.11, 123 minus 0.122. Okay, I just randomly made them up. And remember, each component must have the same number of numbers, right? So like if hello has 3, Daniel must also have 3. Can someone tell me how many combinations of, if you assign this case that each number must have 3, 3 numbers, how many combinations do you think there can be for each token or for each component? How many combinations? What do you think the answer is? So remember, you can choose any single number in the 3 numbers, right? 0.11, 0.112, 0.111113, whatever number. How many combinations are possible? Okay, let's assume it's infinite precision. Correct, the answer is infinity. You can do as many as you like. But normally speaking, you should use not 3. Right, so now the question is, why don't you just use 1 number then? Right, hello can be 0.11. If it's already infinity, 0.11. If you use 2 numbers, isn't it also infinity? Right, so what's the problem? Well, please don't, you should use as many numbers as possible. Try your best to use more numbers. It's because the computer, it's not an infinite machine. So please use like more numbers so it can like learn which numbers to like assign it to. And when you start training a language model, these numbers will be randomly initialized. Right? So like all these numbers will be randomly initialized. And can someone notice my initialization? What is the issue with this? There is a glaring issue, quite obvious, very big problematic issue. Sorry, wait, you want?
I think there's same number for hello and Daniel.
Okay, same number, okay. Okay, good point. Yes, did someone say something? What was the other point? Yes, the magnitude is the most important. Right, 123 and 102 are terrible. When you randomly initialize, please do not initialize with random large components. This will destroy your training. That is why your training might have infinities, and sometimes the training loss goes to 0. Okay, that does not mean your model learned anything. That just means it's some sort of error in your training data, your initialization. So be careful of that. Don't worry, Hugging Face does this automatically for you, so you don't need to worry. And now each component has a list of numbers that it's associated with. Okay, I just use the same number for now, but it's easier for me to do the slides. But essentially, hello, comma, my name is Daniel. Each of them has numbers associated with them. And this is the thing that you're trying to learn for each of these components. And remember, this can be converted into a table of numbers, right? So like if you replace all the commas with just columns, right? These are just tables of numbers. And this table is what you need to train. And again, remember, given the word hello, you want to predict my name is Daniel, right? So like essentially, given that, vector of numbers, can you predict the other vectors of numbers?
Just for clarity,
Yes.
the 3 dots are...
Oh, yeah, you can do as many numbers. So you have to select a option, how many numbers you want to select to represent these numbers. So for example, you can select 6 numbers, or you can select 1024 numbers, or 2048. It depends on the model creator's choice. Yeah.
Every row has to be unique, right?
Yes, every single row must be, well, it doesn't have to, okay, it might not be the case, that might be not, but it should be, yeah, with high probability, it will be unique. Yeah. Wait, is it like, okay. And so, when you do training of a language model, there's a trick that you use, and remember, we want to predict the next word, right? So hello, you want to predict my, right? So can someone notice any pattern with this? Like, why did I do the arrow, and what's the pattern? Can anyone see this? Any special like things with this? No? What happens if you take hello, my name is Daniel, and just shift it up by 1 place? Is it right? If you shift it up by 1 place, hello is now aligned with my is now aligned with name, and so on, right? And then there'll be a gap at the very bottom, right? So we just put EOS, which means end of sentence token. That just means it's the end of the sentence, and we just put it there because it's a gap, right? So remember, machines do not like gaps, and you must use all numbers. So that's the reason why we did that. And this is kind of the training mechanism, right? So we have that list of words, and we want to predict the shifted words. And the transformer, all it does is it's a function to predict that. So given hello, can you predict my? Given my, can you predict name? And so on, right? That's the transformer architecture. It's kind of a bit wrong, but like something like that, okay? Like the FX is like this gigantic model that can be like, there's lots of tuning knobs in it. Okay, let's check if there's any questions. Okay. And the point is, remember the point is we can only predict the future words, right? So hello can only predict my name is Daniel and so on, right? That's the purple component. And the blue box is called the attention mechanism. The FFX, I factored it out, and that is called the multi-layer perception, or MLP layer, right? So there is actually two components in a language model. One does the prediction of the next word, and the FFX, which is the MLP, just does this, changing component. It just makes it like, a bit better than just simple predicting the next word, the attention. Oh, okay, there is a question. I didn't see. Oh, okay, well. Yes.
I know we are focusing on the most canonical approach when we are predicting one token, but you've got papers now on predicting multiple.
Yes, the Facebook.
Comment on this. I don't want to go into the mechanism, but how?
So the comment was, normal transformers predict only one token at a time. How about transformers which predict multiple tokens at a time? Yes, so actually you can predict multiple tokens at a time. It just depends on what is your training objective at the very last layer. You don't have to, remember we shifted by one place, right? Why don't you shift by 2 places and 3 places? Then you'll be predicting 2 tokens in the future, 3 tokens into the future. Exactly. So before it's just one objective. So like one column of the output, we just add more. And yes, you could do multiple tokens. It was the Facebook paper, right? I can't remember. Yeah, it was a Facebook paper. I forgot the accuracy though. Yeah, but yeah, you could do that. But I guess like I don't see any. I guess it's just good for inference time. Like you can predict. You can make inference. If you do 4 tokens in the future, you can predict 4 times faster.
I think they managed to scale model down a little bit.
Okay. Yeah. I think it's mainly for when you do inference, you can do this. If you do 2 tokens in the future, you can have like 2 tokens in one go. I don't know. I don't like that approach. I think predicting 1 token is better because you're already forcing the language model to do so much. You're making it even more problematic. So I think predicting 1 token. Okay, maybe for inference time it could work. Yeah. Yes. Question.
For the multiple dimensions, is that basically for each token, does that correlate to the hidden dimensions in the layer? And because tokenizers do convert it into a single number, right? Like if you actually use a natural tokenizer.
So tokenizer converts it to ID. So like yeah.
That represents then the dimensions, and that's going to be equal to the hidden layers, or is it?
So the tokenizer, when it says like it has 32,000 words in the tokenizer, essentially it's an ID from 0 to 31999, right? So like hello will have ID 2557. So then what you do is you take 2557, go to the hash table, which has this table, right? I made the table, right? So hello has an ID, my has an ID, name has an ID, and so on. And you go to that specific row, and then that is your like sample in your training data. And you do this like for the whole thing. So the tokenizer you do get a number, it's an integer. And you just have to hash it to the embedding matrix, and you will get like a vector of numbers. Does that kind of answer your question? Oh, you're talking about the embedding dimension? So if you see 2,540 or whatever those numbers, that is just how many like columns, how many numbers you want to represent for each component.
Okay, that's the question I had.
Yeah. Okay. Any other questions? Yeah. Yes.
I have
Oh.
one on the.
Oh. Okay.
So you can answer them way later.
Okay. Yeah. You had a.
Just following up on that, I never understood what's the significance of what is the difference between 2048 versus
4096. I guess it just depends. Like if you make so remember we said how many combinations can we do? Infinity, because we can do because floating representation. In theory, if you have infinite precision, it can be infinity. But someone mentioned how depending on the precision of your float, it's actually limited precision, right? So like the point is you want your model you want the training objective to actually learn, give it as much freedom as you like, right? So like if you're trying to restrict the model when it learns, it might actually not be helpful. And that is why normally people have like these large numbers like 6144 embedding dimension or 8192 embedding dimension, right? The more numbers you give it to the model, it just has more freedom to move. So if, in theory, in theory, it should have better accuracy. In theory, everything's in theory. I don't know if there are research papers which show this. I think someone should write a research paper on that. Each embedding dimension, test, do 3 trillion tokens. Okay, that's probably too many. And then see which one has, I'm assuming the more you add, the higher accuracy. Yes?
Well, people used to do like one-hot encoding where your embedding layer would be the same size as like your vocabulary. And I think that like a denser representation does work better. So I think there's like a sweet spot somewhere in the middle. I don't think as you get larger, it's always better.
I agree on that. I think someone needs to do a research paper. Yes. That should be a new research topic. I've never seen this paper before, so like that would be very interesting. So yes, question. Yes. The reason for that is it just makes training faster sometimes. So depending on, so there is, I think Andre was the one who tweeted about depending, if you pad the token, if you pad the vocabulary to a specific number, you can actually make training faster because in the NVIDIA GPUs, when you use tensor cores, if you pad it correctly, it can get the data and cache it more appropriately. So like, for example, the cache size is like 64. I think it's 64. Okay, maybe I'm making stuff up. But like essentially you have to pad it to a multiple of 64, something like that. And so sometimes that happens. Another one is like some people want to add, when you want to do more fine tuning, when you want to like train the model for more, you want to use one of those unused tokens for your own purpose. And so they left some holes in there. Yeah. Does that kind of answer your question? So when you do tokenization, assuming you don't encounter these tokens, you won't have any problems. But if you do, then there are problems, yes. So for example, if you do Llama 3 fine-tuning, if you use the base model for Llama 3, and you accidentally use one of those tokens, you will get nans for fine-tuning, right? So you have to be very, very careful. And so like I think what we did is for Unsloth, we actually find these untrained tokens first, set them to the mean of all the embeddings, and you won't have these issues. So I think that's actually a model creator's problem. It's like they probably should have not set it to 0. I don't know why they did that, but anyways, yeah, they should have set it the like a normal distribution or like some just random initialization. Yes, this is kind of yeah. Okay. Any other questions? Okay. Oh yes.
Why was there an US and not a VUS at the beginning? Like, what if I want to, you want to learn that hello is like for most sentences that they start with hello, so why do it have a beginning of sentence token?
Oh yeah, you can put a beginning of sentence token. I just didn't do that. You should put a beginning of, most language models will put a beginning of sentence, like what is it, I put the end of sentence, you should probably put a beginning of sentence as well. That's actually very important as well. Most models do that now. They find that to be very helpful. To be honest, I don't think so it's actually that effective. I think the beginning of the BOS token came from the old style, the CLS token for, I think it was the first token for like BERT style. So like they had a classifier token at the very start. I think it was at the very start. I'm not 100% sure. But I think that's where it came from. I don't think so the beginning of sentence token actually makes that much difference. But you should put it. You should put it. Giving the model more freedom to move is always better. So yes, I probably should have put the beginning of sentence. But yeah, for demonstration, I did not do that. Yes, okay, we did that. Right, so like the green one, right, so like the attention block is kind of encoding the stuff that we described, right? Predicting the next word based on the previous words, right? And so like the attention block is that first part, the MLP block is just the mixing pump component. And this is kind of the transformer architecture kind of like in visualized. And you just repeat this L times. That is a transformer. Now, another question I always have is, why is training language models not O of n cubed? Because like, aren't you like, given the word hello, you're predicting my, right? And now we have hello my, you're predicting name. And then you have hello my name, and you're predicting is, and so on, right? Shouldn't this be the training data? why is the training data just hello my name is Daniel EOS, right? This is the training data that you actually see. Why is it not this? Does anyone know why?
Complexity?
Sorry?
The complexity?
The complexity?
Yeah, so it will be...
Yes, the complexity, yeah, very bad complexity, right? So like, if the sentence is like but if the sentence is like 100 words, what do you think? How many? Quite bad, yes, basic one, yeah. So like 1 plus 2 plus 3 plus 4 plus 5 all the way to plus 100, right? So like n divided by 2, 1 plus 100, I think? I can't remember my maths, but yeah, something like that. So it ends, yeah, it's very bad. And that's if you have one sentence. What happens if you have like 10 sentences? Oh my. Yeah, but like, does anyone know why language models don't need to do this? Like, we don't actually need to do this, right? So like, we can skip, essentially, instead of having this as the training data, your training data is simply, my name is Daniel, and shift it by 1 up, and that's your training data. Why is it not this? Oh yes, we haven't talked about position encodings yet, yeah. Okay, but you don't need position encodings. Oh, okay, yeah, attention, what? Oh yeah, the attention mechanism? Oh, correct. That's the answer. Yes, it's because of attention. Well, actually, specifically masked attention. Right? So that's a trick. Okay, we'll be talking about that. We'll be talking about it a few times. And I'll give you the code again. Well, actually, the maths formulas for transformer architecture. Right? So like attention block. We will be now talking about the attention block. Right? So like the Z is equal to the softmax of QK transpose over root H plus M V. And as you mentioned, it is the attention mechanism which allows us to skip the O of n cubed complexity and make it O of n squared. Why? Because remember, we want to mask out future tokens because we don't want to predict on future data, right? So like by using this mask, weirdly, this mask allows you to train more efficiently. It's funny because like attention is O of n squared. So the longer your sequence is, the worse the complexity. But actually, there is a special trick which you use a mask, and this actually makes attention not that bad. So instead of doing hello to predict my and so on, so on, so on, the attention mask acts as this methodology, right? So the attention mask itself acts as, you don't need to do like all the complicated, all of the words predict the next word. Probably should have. So we'll be now talking just about the attention itself, right? So like softmax QK transpose over root DV. Just a reminder that whenever you see QK transpose, a query and keys, I do not like to there's actually explanations like what is a query, what is a key. I do not like that actually approach. I would like this to be a maths approach. So my view is, given the matrix X, which is your embeddings, right? So remember, hello is a vector of numbers, right? You multiply this by some weights, WQ, WK, and WV, and you get back QKV. Q is query, okay, keys and values, but that's a very vague interpretation. I don't really trust those interpretations. It's not that clear. Just assume it's just maths. Okay, just like get your X matrix and multiply by weights, and you get some extra weights. That's my view. And so that is kind of, so like if you see why I stacked it like this, does anyone know why I stacked it like this? Like why did I present it like this specifically? Why is it like the presentation like this? Any points?
You want to put the composition?
Sorry, one.
You want to put the composition?
Composition?
Decomposition.
Decomposition. Yeah. Interesting. Okay, that's a very interesting point. But no.
You're just lining up the dimensions of the multiplication?
Correct. Yes, that's correct. So I just lined it up such that it's easier to see. And if you take the matrix X and you multiply by WQ, you'll get Q, right? And this is actually the correct maths dimensions and stuff like that. And so like I like to normally tell people to like visualize transformers as maths. It's actually, in my view, it's easier. Okay, I'm not sure for other people, but my view is easier. I do not like it when they say, oh, queries and like you're trying to do keys and values. I don't even know what that even means. Anyways, and the yellow components are the ones you want to train. X is what you want to train. WQ is what you want to train. WK and WV. And QKV are just the components afterwards. When you have so remember, you have the Q, you have the K. All you need to do is when you do K transpose, you transpose the matrix, and you do Q times K transpose, and you get this big square matrix. called QK transpose, right? Hello, my name is Daniel, and so on, right? So like that's kind of what I want to visualize is like, it's actually when you do QK times K transpose, you get a square matrix. And all you need to do now is do the softmax divided by root D, right? So softmax, essentially each row you normalize to 1, right? The sum of the exponentials must be, right? You need to like normalize them. Does anyone know why you should do that? And why should you use softmax? Any clues? Why do, yes? Yes, okay, that's the answer, yes. But like why? Like why?
Because when you multiply them, you can get out of hand.
Sorry, when you multiply them, you can get nans?
No, you can get out of hand and get loads of exponentials.
Oh yes, very good. Oh, that's, okay, do you know how to fix that?
Well, that's the point of the softmax, isn't it?
Close.
Okay, then I'm out.
You have to minus the maximum of the row. That's how you fix it. Yes. Oh yes, very good. Okay, yes, we're gonna sample from that. Okay, sample from that distribution. But what happens if you don't do the softmax? Doesn't this still work or not? Like, what happens if you just do QK transpose over root D? Remove the softmax. Like, why do I have to do softmax? Yes. Interesting. Then you can fix that with like minus max of the row as well, with exploding. Anyone else? Okay, what happens if you don't have a nonlinearity then? So does it have to be softmax? Can it be something else?
Theoretically, it could be something else.
Yes, it could be. Yes. That is another active area research which people should focus on, which is like, why do we need to use softmax? Generally speaking, research papers show that is actually the most accurate. If you use other activation functions, it might actually not be that accurate, right? So like, but this also is the bottleneck of transformers, is because it's a softmax, it does the row sum of the exponentials. This means that you can't actually decompose this, right? You can't actually bring the matrix multiplications out. And so if someone can find ways to make this faster, you get like millions of dollars. Okay, maybe like much more than that, but yes. And V is just, remember, the V comes from here, right? So we just take the V, multiply it up again, and we get this matrix at the very end. And that is, right? Yeah, that is the final component, right? This empty box is what you get out from the attention mechanism. For the layer norms, I don't really want to explain too much, but the layer norms essentially, you take you square all the elements per row, you sum them, you divide them by the square root, and you take the mean and they just do 1 divided by, right? All this does is just normalizes the rows to make it easier for the language model to learn, right? So like, why do people do layer norm? It just makes training easier. It's more stable. There's no other point. There are like some theories of like, batch normalization, like, out of distribution, you want to make like shift towards the distribution for out of distribution data. I just like to think of this as an optimization method. Layer norms just make training easier and more stable. And layer norm is simply, remember, as I said, is you take the X matrix, you do a row sum of all the squares, and you take the mean, and then you just divide it, and then you multiply by some weights. It's a vector of weights, and that's just layer norm. You don't worry too much about like what is layer norm or what it does. It just does training better, more stable. Please add as many layer norms as possible. Yes, add everywhere. Layer norms everywhere, and you'll make training much better. Okay, I don't know if you can see this. But in Triton, right, in order to write Triton code for the layer norm, this is the forward kernel. We will not be talking about Triton today, but it's actually not that complicated. If you read more intently, ignore all of the components. There is only very few lines for the layer norm. It's actually not that complicated. The rest is simply just how to load the data. It's actually not that hard. Yeah. The backward kernel is when the problem comes. How do we actually do the differentiation of the layer norms? Right, remember, you have to train the W, right, is yellow. You actually have to train that. How do we find the derivatives of the W? It is very complicated. And if you want to learn in your own time, you can have fun learning the derivatives. It is extremely complicated because there is sums, there is row sums. How do we do the derivative of a row sum? It can get quite complex. I wanted to talk about backpropagation today, but I thought it's probably too heavy maths. So no backpropagation, but we'll be showing, but I do have tutorials on that. So if you go to the Triton tutorial, I followed that. That's actually quite helpful. And the backward kernel is just very, very problematic. Now, up to the rope embeddings. Why do we do rope embeddings? Does anyone know what is a rope embedding? Yes?
It's a way to extend, context, right?
So you could use the rope embeddings to extend context, yes.
Okay, that's not what
Do you know
it
how?
is.
How does it extend context?
So, well, how does it work? Versus
Well-
yarn or
How would you use rope embeddings to extend context? What would you do?
how would I do that?
Mhm.
I would create basically what I would do is I would basically create kind of a
You just multiply the base by 2, and then you get 2 times longer context. You multiply the base by 10.
The problem is if I'm looking for 1 million contexts, right?
Mhm.
Then the model falls apart if it's trained at 400.
Correct.
4K, right?
Yes.
So that's where yarn might kick in.
Yes.
Instead of
So is that the dynamic?
well,
Yeah.
that's static or dynamic.
Yeah.
Either way, right?
So how would you solve the problem if it's like you want to train, if you want to have 1 million context length, but your data set is only 1,000 words? How would you solve that problem? How would you think of solving that problem? Because some people have said they do 10 million context length. Is there any data sets which is 10 million tokens? How would you?
15 trillion tokens, fine wine. So we have that.
Oh, no, but that's 15 trillion tokens for the data set. I mean, how do we do long context? Remember, when you do long context training, you have to have a document which is at least 10 million words for it to learn how to predict the 10 million plus 1 token.
So how I would solve the problem would just be to gather better and more diverse data sets. But
Yes, that's
that's
the.
the ideal.
So what happens if there is no data set which is 100 million tokens? Then what would you do?
If there is no data set that's 100 million tokens, I would synthesize.
How would you synthesize if the model, it's like a chicken and egg problem.
Huh?
How would you do synthesis?
So no. I would basically just create. I would basically use Claude or any of the state-of-the-art models with LoRa, and then basically turbulate the data.
But are they trained on 10 million tokens?
Huh?
If the model itself wasn't trained on 10 million tokens, does it do long context?
So if I was to try to solve this problem for client,
Mhm.
for example, let's say their code base is in 10 million tokens, or and they want a 10 million something context or whatever,
Mhm.
right? Then I would basically create a
Synthetic data set?
It's not synthetic, but a derived data set from what we have.
Okay,
So
interesting.
assuming we do not have, but I can't assume that we have no data, right? So
Good point. Okay. I don't know. I think it remains to be seen. Many claims by companies, 10 million contacts, 100 million contacts. I question.
well, I've only seen 1 million actually work, so
Yeah.
and that's ring attention in theory, right?
Okay. Now we're going into. Okay. Yes.
Sorry,
Okay.
apologies
Yeah.
again.
Okay. No. That's fine. I was asking the questions, but okay. Wait. The question was what is a rope embedding? Someone did mention positions. What does that actually entail? What do you think is the point of a rope embedding? All it does is you want to tell the model to learn what is the position of the words. Right? So hello, my name is Daniel. It actually has a meaning. Hello is the first token, right? But then if you put hello as the third token, what's the difference? There is a difference, right? So depending on where the word is in the sentence, it matters. So the whole point of embeddings, rope embeddings, is it tells your model to learn where is the position of this component. And old style, they use absolute, relative, absolute positions. Rope embeddings does some special tricks, times a cosine plus a sine, times a sine, and does some sort of special rotation and stuff like that. The paper found that if you do rope embeddings, it actually has high accuracy, and everyone does rope embeddings now. Yeah.
Why do we need capital cases then if we already have the positional information in the embedding?
You mean the position?
At the very beginning, you mentioned that there is a lowercase version of bird.
Yes, there is. I think BERT did not, I don't know, did BERT use rope? I don't think so. BERT used absolute, yes, that's the problem. I think BERT used absolute. I think, I don't remember anymore, but, oh yes, exactly. So rope did not exist, yeah. And so like this paper, the Roforma paper shows, so previously people use absolute position encodings, which simply just adds a position. Like you can literally just add, like if the position is 0, just add 0. If the position is 1, add 1. If the position is 2, just add 2. That's literally what they do. Well, actually, well, not exactly, but like, you know what I mean, right? You have to divide it by some sort of normalizing factor, right? If the position is 30,000, don't add 30,000, right? You would like destroy training. But that's kind of what they do. And what they show is if you do rope, you can essentially increase accuracy somehow. And we just use this as gospel. We just treat this as true. And everyone uses rope now. Yeah.
In that case, do you have an opinion on yarn versus rope and yarn dynamics?
So yarn is kind of rope. So yarn just does, I'm assuming yarn is rope, but it does like, actually, I don't think I should comment on this because I'm not an expert on that.
Okay.
Doesn't it does like, it does, yeah.
So I'm no expert on, obviously,
I'm not expert on long context.
On rope versus yarn, but since VLM only supports static yarn, unless you're planning on trying to go to 1 million contexts, it's actually kind of terrible. So,
Is yarn the one which does like the base like randomly changes? Like if you have like up to 1 million context and you do 1,000,001 context, the base changes with that, like the factor changes. Is that yarn?
that's
Dynamic changing, yeah.
So, and that's the issue is that in like, let's say 5-shot, right? That's not even a short 5-shot, right? That's not anywhere close to 1 million contexts in theory, or maybe like, let's say a 3-shot or 2-shot. Like, so.
Did it?
But obviously dynamic yarn in theory could fix this rope issue where like we just take this rope as gospel where but are you following kind of my question here?
Yes, no, I think dynamic yarn is just rope though. Like, okay, that's weird. Okay, maybe I'll unplug and replug. So like the screen kind of went away. Let me just do this again. Is this like, is it not working? Or is it like screen or no screen? That's weird.
Can you answer questions while we're at it?
Oh yes, okay, yes, I'll answer some questions. Yeah. Anyone else have questions? Wait, okay, wait. I need to refresh the. Oh, if anyone has like take a break, you can take a break now if you want. And if you have like other questions, yes, okay, question.
So I don't know about yarn is what seems some of the discussion is like trying to extend the context window of like rope, am I right?
Sorry, yarn is.
So I don't know what yarn is, but I was hearing some stuff about like extending the context window, and I'm just wondering that like what is the issue with like rope when it comes to like the context window? Why isn't it like not just have like infinitely like a very big context window? Is there a problem in like doing that?
So the question is for context windows.
Like what improvement is like yarn on like rope? Like what is like?
Oh, okay, what is the improvement? Okay, so the point of yarn, like what we were talking about is like how do we make a language model learn, how do we make it do long context without training on long context? Kind of, yeah. And so like what yarn does is you can essentially extend the context window automatically by dividing the base of the rope embeddings. You change the scale factor. I don't actually have slides for this, but it's just a methodology which allows you to scale the factor and you essentially magically make the model learn new context, long context. That's kind of what yarn does.
And you originally wouldn't train on the long context simply because it's expensive?
Yes, it's extremely, if you do 1 million context length, then your O(n) squared is 1 million squared, which is horrible. There are like some other methodologies, like, they want to do like linear transformers and like, yes, I guess you could try that, but I don't suggest that. Yeah, so sorry, question.
I would be very interested, Daniel, on your comment for the fine-tuning versus in-context learning from low-level perspective.
What is the difference between in-context learning and fine-tuning? Or what's the benefit?
How does
That is a good question. So fine-tuning changes the grade. You have gradients for fine-tuning. So yeah.
I
my
Your opinion, what would you do when?
I think it depends. I think I would do in context learning first. So if you have like few short prompts, you shove it in to see if it works. But I would still resort to fine tuning if you want to be more efficient. And if your model doesn't seem to be learning, then you have to go back to fine tuning. There was a paper which was released yesterday, I think. Was it yesterday? It showed that in context learning is very useful. And it like learns kind of like how to be like a random forest or like a tree. I think it was yesterday, the paper. That was quite useful, very interesting. But I think fine tuning is still very important, especially if your model is not learning anything and it doesn't seem to be working, then you have to like use fine tuning to change the behavior. I don't really have a comment on this. Like I just feel like you should do everything and try everything. Yeah, any other questions?
Well, I have a couple in the app. I don't know if...
Oh, did you? Okay, I think my app kind of glitched.
Do you want me to read them off one by one?
Oh, maybe I'll okay, wait. Yeah, wait.
I'm
Okay.
sorry, I asked a ton of
Okay.
questions.
Okay, maybe, okay, let's just, I'll continue and then we will do the questions.
Sorry, it's
Yes.
back, so we're good.
Yeah, okay, I probably have to, okay, I did not see time. I've been speaking to, okay, anyways, that is the rope kernel, and it might look horrifying. It's actually not that bad. It's literally just the formula that it did, Q times cosine plus Q times a rotation matrix times sine, and that is just rope. It's actually not that hard. Just the code is a bit more annoying, but it's just like moving the data. It's just data moving and moving data and stuff like that. All of the code is just related to data movement. So not that complicated. The most complicated part is the derivatives for rope. And you have to use something called rotate half, which essentially rotates half of the, so, okay, just read the code. It's like minus x2 concatenated with x1. So you essentially take the matrix X, you divide it by 2, you take the first half, you put it on the second half, and you switch the ordering, and the first half becomes minus. And the code generally is reasonably well, hopefully, for understanding. But the question is, and so this is Hugging Face code, right? So like Q times cosine plus rotate half Q times sine. The question is, how do we actually find the derivatives of this? This was actually a very complicated phenomenon because I could see many implementations not doing this correctly. And it is very special, the derivative. Simply, if you notice, is rotate half, the function, is literally a matrix multiplication, right? It's Q times R, where R is a rotation matrix. And the rotation matrix is minus identity and identity, and zeros on the diagonal. And if you do this, because it's a matrix notation now, simply the derivative is the transpose. And so if you do the transpose, the minus sign just flips. And if the minus sign flips, it's literally the same as your previous example, just put the minus. Okay, I probably explained this too quickly. But the point is, if you do matrix multiplication, you can derive derivatives very simply. My suggestion is shove the derivatives in Wolfram Alpha or your favorite tool. You can use ChatGPT as well, and you will get the derivatives back. But you must put it in the form that's useful for the computer to see. Now we were talking about the MLP component, right? So we completed the attention, we completed the rope, the layer norms. The MLP is just a mixing component, right? So it's an activation function times some weights, multiply some of the other weights and stuff like that. All it does is it mixes the signals to make it more fancy. In theory, you don't actually need the MLP component. Like most attention, you don't actually need this part, but you must put it for the model to have more freedom to learn. And the famous paper, GELU variance improved transformer, very famous author, I'm assuming most people know him, but he showed that if you add GELU, SWA, and all these other variants, you can actually increase accuracy. Once again, this is just treated as fact in the machine learning community. We should be doing more experiments than just using this methodology, but we just treat it as fact. And this is in Transformer++, the architecture which everyone uses. There is a very big difference though. In GPT-2, they don't use the GELU variance. They simply just use a normal MLP, right? So X times the weights up, do some sort of activation function, and then you down project it, so the weights down, right? But then if you do SWA and this new variance, the GELU variance, you essentially add this component where you do element-wise multiplication, and then you do a down projection. So it's actually very similar to the GPT-2 architecture. You just add an extra component. And so I try to there's also a naming change, like up and down, up and gate and up, changes and stuff like that. But in general, you can see it's very similar, just the extra element-wise multiplication component. Yeah. But there is a new, the Numitron paper, for example, the Numitron, the new model by NVIDIA, did not use GELU, and instead they used squared ReLU, right? And they showed that you don't actually have to do GELU anymore. You can just use squared ReLU, and it seems to do okay, although it remains to be seen if it actually is good. But yeah, so they showed that if you do squared ReLU, you can remove this, you can essentially go back to the GPT-2 architecture, right? You don't need to use Llama architecture anymore. So Llama and Mistral, Gemma, all used the second equation. GPT-2 used the first equation. You can go back to the first equation, but the trick is the F must be very special, and that's called squared ReLU. And they showed that if you do this, your accuracy does not degrade that much. And so, yes, the paper. And interestingly, if you see one of the authors, it's the same author. One of the authors' names is similar, the name is the same. So, they were also the ones to showcase the squared ReLU. You don't need to do GELU anymore. And you can simply just use squared ReLU as well. There is a research paper which I highly suggest people to read, and it's called The Physics of Language Models. It is extremely long, though, but it has many nuggets inside, and I highly suggest people to read this. They show they actually did so many tests and experiments, and they showed that if you used GELU variants or gated MLP, it actually reduces the model's capacity to learn on small models. Okay, so that's the point. It's on small models. On small models, if you do GPT-2, the first formula, it does better than if you do Llama, Mistral, or Gemma, the second formula. Only on small models, right? That's the point. Only on small models. And there are other special things inside the paper which I highly suggest. It's extremely useful. For example, they say that for example, the activation function, which activation function did you use? Should you use the SCILU or GELU or ReLU or whatever? That's not that important, right? So it's not that important. If you use biases, it's not that important. So there's so many different things that you don't need to do. The paper shows, but people just treat it as gospel. Oh, we have to use this specific component. My suggestion is, we should do more testing in the AI space, which variants are the most important. But I think this paper is pretty useful. The code for the Swiglu kernel that's the forward kernels. Again, it's not that complicated. The second part is actually useless. The Swiglu kernel is literally 3 lines. It's just the 3 lines which are commented. The rest is just data loading. How do we actually load the data into the GPU? It's not that important. And if you use Torch to compile now, you can simply generate these kernels automatically. And this makes your training much faster. So that's what I suggest people to do. Just use Torch to compile. You don't have to rewrite Triton kernels. Yes? Sorry, WK? Oh, gate. Oh, it's just another matrix. So W gate, W up, you train this, and W down. These are all you train them. W down, W up, these are all you train. They're just numbers. So matrices, X times W gate is so remember the, this thing. Right, this is for attention, X times WQ, WK, WV. Assume it's just W gate, W up, and W down. And it's the same thing. So you just train these. Does that kind of answer your question? Or? Oh, no. It's just a naming convention. W up is just, it's actually called upper projection. The naming convention is like WB, WA, WC. It's just a naming convention that people like to use. W up, W gate, and W down. They do have meanings. So W down is a down projection. Up means up projection. So essentially, you take the matrix and you make it larger, and then you project back to a smaller version. It just makes the model better to make the model have capacity to learn. So it's just a naming thing. Any other questions? Okay. As I said like before, the derivatives are always a pain. If you do the derivatives of SWA, it is a nightmare to do, and I do not suggest you to do this. But I had to manually do all the, you can see all my comments, so like the comments are actually there. If you do see more carefully, I wrote it in math formulas of how to actually take the derivatives, and it's extremely painful. I highly suggest you not to inflict pain on yourself by doing this. It took me many days to do. So do not, I don't suggest this. Yes, question. That is a very good question. So I use Desmos. So Desmos is a online graphing calculator. You type all these equations in, and then you can see does the graph align. Oh, every single component, you have to be careful. So every single component you have to check. Oh, is this component correct? Is this component correct? Check all of them. And so like I normally, so like you isolate each component separately and then test it. I'll talk about that actually. Yeah. Any other questions? No? Yes. Okay. And this is the cross entropy loss kernel. I'll probably just skip this. Don't have enough time. So I wrote this as, if you want to inspect the formulas and stuff like that, how do we do the derivatives for this? You can do this. It's not that complicated. Actually, it is very complicated. I did spend a lot of time trying to like work out the derivatives. It might be a bit foreign for some people for the derivatives. The main reason why it gets complicated is when there's sums, right? For like whenever there's sums, I dislike, doing derivatives when the sums is always painful. Matrix differential is actually very easy. If you do x times w, the derivative of w is just x transpose. It's very simple. But if you do derivatives when the sums, it's horrible. Yeah, it's quite horrible. What you can do for the sum when you do derivatives, if you transform the sum into a matrix multiplication. Right? So a sum is just x times a vector of all ones. Right? So that's called the row sum. And essentially, if you do this, you can actually make differentiation much easier. But I won't be talking about that. That's for another topic. And someone was talking about stability for softmax. If you minus the maximum of the row, you can make softmax much more stable. And this is to like reduce exponentials of large numbers, and then essentially it takes over the entire exponential, right? And so like if you do this trick, when you minus the maximum of the row, this makes training much more stable. Always do this. Yeah, always do this. Yeah, and that's the code for the forward. Not that important. Oh yes, I wrote the code for the backward as well. Oh wait, so this is the forward. And it is quite long, but I wrote all of this down for your own leisure. If you want to read and implement this, have fun. But I wrote this step by step, right? So like, take y is equal to log sum of x. Then I simplified it out. Like, if you exponentiate both sides, right? You can do exponential of the y is equal to the sum of exponentials, and so on. All right. And so like, I wrote this all down. But there is a methodology which we showed in Unsloth, as you can use chunked cross entropy, and this is actually very helpful for large models. Your logits are very large, so if you chunk them, you can make multi-threading much better for the GPU. And so like the problem though is like the derivatives, the forward propagation, you have to be careful now when you do chunking. So like essentially you divide these into slivers and parallelize each component. I also wrote some maths and stuff like that for you to review. And how you actually do the chunk sum is very interesting. The log chunk sum of the log sum exponentials is just the log sum exponentials. There's like, you have to do some manipulation, and it's actually very interesting. You don't actually need to change that much code to make it work. Okay, now we'll be going to the next component, which is to investigate the Llama architecture. Hopefully this works. Yes, question.
Chunking, is that something that you guys wrote as a part of Unsloth, or is it right now a part of Pytorch or something?
It is part of Unsloth currently. I think I heard that the Pytorch team will be including this in Torsia compile, although I'm not 100% sure. This reduces memory. This makes large vocabulary sizes work. So the biggest issue why you have to do chunking is CUDA, NVIDIA GPUs has a limit, 65536. I think that's 2 to the power of 16, or I'm not, I think so. Yeah. So there is a limit. And so if your vocabulary size is larger than 65536, you must do chunking. Yeah, you have to do chunking. So like if you I think, was it Gemma? 128,000? Or I'm getting confused. I think it's 128,000. You have to divide it into 2. And so like your chunks would be 2. So it should be in Pytorch in their future release, maybe. Yeah. So now we learned all of this. Now you can read the code for Llama. So if you go to the code, like modelingllama.py, it should be in the slides. But you can also type in Google, like modeling, modeling py. This, right, there is your, if you go to line 94, you have your rope embedding, which we talked about, right? Just assume, don't worry, okay, I probably use my mouse. Yeah, okay, I don't really like how GitHub does it's kind of annoying sometimes, but I think I can disable it if I log in. Anyways, the symbols. So if you go to this, right, this is not important. If you go to the first one, is line 74, the Llama RMS norm, right? This is the layer norm kernel, right? This is the code for the layer norm kernel, just this much, right? This is you take the row, you take the sum of the row, you take the squares of the row, like each row, you sum them, you divide it by the mean. Remember, this is the only reason why you do layer norm is to make training more stable. And it's actually not that complicated, it's just these few lines. The rest is just bloat code for like, you have to set stuff up, you have to do random initialization, blah, 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 comments and stuff like that. But that's the layer norm kernel. The rope kernel, the rotary embedding is a rope kernel. This is just setting stuff up. This is setting stuff up. Forward, right? This is the most important component, which is the forward component. Now, don't get scared by this. That's because we fixed a bug. So this is actually our bug fix that we did. So this is all in transformer architectures. Is like you have to be very careful when you downcast to float 16 if you use B float 16. Right? This is actually very important. Before, you have to be very, very careful when you use float 16 and B float 16 training, mixed precision training, because it will downcast incorrectly and your rope embeddings will be wrong. So it's not supposed to look as ugly as this, but unfortunately, it looks ugly now. Before, it was just this, right? But this is just setting up code that we have to like fix the bug and stuff like that. Yeah. So it's actually not that long, right? So like it's just this, yeah, up to here. So whenever you see these architectures, it just looks complicated, but it's like, yeah. No. So there are like if you do Torch and compile, we're still like, I think 30% faster. So no matter, sorry, if you use Torch and compile plus Unsloth? Oh, we're still 30 times faster. Oh, sorry, not 30, 30%. So we're 2 times faster than Hugging Face plus Flash Attention 2, but Torch and compile, they're adding kernels from multiple packages in. So yes, they could learn from Unsloth and put it in. I'm assuming they're doing that. I did have a talk with them, so yes, they're probably doing that already. But yes, we're still 30% faster. There was like I think someone tested this last week. Yeah. Any other questions? Okay. This is not important. This is the one we're talking about for linear scaling for rope embeddings. If you want to extend the context length, that's kind of what they do. Right? This is for scaling, not that. There is a rotate half part, which I was talking about. Right? How do we actually derive the formulas for the gradient? How do we actually do the rope embeddings? It's just this. The MLP, which we talked about again. Remember the MLP layer? Right? So there's a gate projection, the up projection, the down projection. This code is bloat again. Ignore this. It's just this. It's just one line. The rest is bloat. Ignore that. Right? So like the down projection is just the down projection. Right, the activation function, the gate projection times the up projection, right? So that is the MLP. That is the swiggloo, one line, not all of this. That's just for training purposes. Repeat KV is just that's for like okay, I won't explain this too much, but that's for the attention part. This is just to make inference faster. When you do QK and when you go back to slides, if you go to where is it? Right, WQ, WK, and WV instead of training WK and WV, you train a small sliver and you repeat this. And this can make inference faster. And so like we don't actually train the full the matrix size WK anymore. We train a small sliver, and we just repeat this. The attention, again, all of this is just preparing, right? This is just preparing, right? And okay, ignore, blah, 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 bloat, get rid of this. Don't look at that. There is Q, K, and V. That's the matrix part. There is the only problem I find that people struggle with is there is like dimension manipulation. You have to like manipulate the dimensions of the output. That is actually kind of annoying. I do agree this is actually very annoying. But just assume it is this, right? That's all we're trying to do is this. And that is just these 3 lines do this, and then we want to do QK transpose, right? Oh, you have to apply the rope embedding. Don't forget to apply the rope embedding. And then QK, that's a repeat KV. Repeat KV is the one the trick that I said to make inference faster by repeating so if you go back here, the K and the V, you take only small slivers. You only train small slivers and you repeat them 4 times. And it does not reduce accuracy that bad. And that's the repeat KV. This is the QK transpose, right? Torch on map ball, QK transpose. This is the attention part. Softmax, dropout. Okay, no one uses dropout anymore. Get rid of that line. Matrix multiplication, right? So this is, so up to here is QK transpose over root D softmax times V, right? So up to here. And then we do some and then we have to do some output projection as well. The rest, okay, whenever you see this part, just ignore that, right? Whenever you see like if self.config.pretraining TP is more than 1, this is just for faster training, so you can get rid of that. Well, not for faster training, for like, training across multiple GPUs. You can ignore that and just assume it's just that one line. Now there is more code like flash attention 2, ignore. That's just for faster flash attention. Ignore. Right, no, you don't need to see this. Scale.product attention is a faster version of attention that is native to Pytorch. Also ignore. You do not need to see that as well. Pretend you didn't see that. And then finally, we get to the decoder layer, right? Remember, we show, okay, wait, maybe I should exit the slides. Where is it? No. So remember the decoder layer. So this, right, remember we said we repeat L times, right? This is repeat L times. This is just shoved in the decoder layer, right? We call this one decoder layer. And again, we do the layer norm. Remember, put layer norms everywhere. Do layer norm, do attention, add some residual. This also makes training more stable, right? When you add residual, it makes training more stable. Do more layer norm, do an MLP, add more residual, and then we complete it. Right? That's one component of the decoder. And remember, we repeat this L times. And the rest of the code is just doing this L times. Now, where is it L times? Comments, forward, right? You go to forward. Yeah.
To the previous one. So does it make any difference where you put the layer norm?
In my opinion, put it everywhere.
Yeah, but in terms of calculating the residual and then adding it by.
Oh, that's just by. Yes. Why is the ordering? I think it's layer norm first, then add residual. Is that correct? Or maybe I'm getting confused.
So it's get residual, then norm, then calculate the attention, add back the residual, and then there's probably another norm somewhere down the line.
Yes. The ordering, to tell the truth, it doesn't really matter. I think there are some research papers which show if you switch the ordering, it maybe increases, like it decreases accuracy by like 0.01%. To be honest, we need to do more testing again. Like, in my view, shove layer norms everywhere. This should make training more stable. But it makes training slower. That's the problem. That is the only problem. But I suggest you to put layer norms everywhere. Wherever you see it, just shove layer norms. Yeah, layer norms always work. Okay, and
So just one more thing then. Why isn't this an issue that you get the residual before applying the norm and then after, like, you calculate the attention
So why do you add the residuals of the previous? So you take the you save the state before the layer norm, and then you do a layer norm, and then you add back it in. So why do we have to do that? Is that your question?
Yeah, why the normalization is between that rather than before? Like,
Oh, you could do it before if you want to. You could try it. It depends. I think it's for, yeah, it depends. As I said, all of this is like gospel, like, oh, why do we do this? It's just people tried it and they said it works.
I just meant why this isn't an issue, but I guess.
Oh, what do you mean by not an issue? Like, why does this work? Or why is this like not a, what do you mean by issue?
I mean, the normalization kind of changes in some way, the representation.
Yes, it scales it. Yeah.
Right? So you're combining something from before that change with something after that change. And why is it compatible, basically? Why
It's just maths. You just let it, it just works.
yeah, I get that.
Because if you do that, the autograd engine will still know that you did it, and the derivatives will still be applied correctly. So you just assume that it works. To be honest, that is another research topic. You should try that. I'm being like serious. Like, there's so many research questions that are like open. Like, why doesn't everyone just put layer norms everywhere? Like, why don't you put a layer norm after the multi-head attention? Put a layer norm after the squiggler. Put a layer norm after the inputs. Put a layer norm, everywhere. And my hypothesis is it makes training more stable, but like it makes it slower though. Yes.
In theory, could mechanistic interpretability solve, like, not solve, but explain this?
Do you mean like, what do you mean by like explain this?
Mechanistic interpretability where you take the
Which method? Do you mean like doing the autoencoder style, like sparse?
lens, or like just direct weight, just looking at the weights and what happened at inference time or training time?
Do you mean like the, which method, like the, because I know there's like many methods for mechanistic interpretability, like there's different types of methods. Does the sparse autoencoder one or the?
Well, transformer lens is Neil Nanda's tool.
Okay, I have not used that, sir. I'm not an expert on that, but.
So, but you can see the literal like activation.
Yes, the activation one, yeah.
Yeah. So basically, I mean, I'm gonna not diverge from this, but so basically, do you think we can figure out why this works this way? Like, because you said it's kind of an open question, right? But do you think that using tools like transformer lens, where we can look at training activation, or not activations, but like steps, where in fact we would have to like, I'm not sure if I'm explaining myself correctly, but like, do you think mechanistic interpretability is a path to understanding this?
Good question. Could mechanistic interpretability, okay, it depends. I think my view is it just layer norms. If it's specifically on the topic of layer norms, it just makes training more stable. I don't think so it has any like meaning, like, that's my view.
Okay, that's fair.
Like, I think like the math equations don't show that it has any meaning. I just find it to be just stabilized training. There was like papers like the, what was the one? Batch normalization. I forgot what the term was. Yeah, like there was like a theory which shows that batch normalization reduces problems of out of distribution data and stuff like that. Reduces internal covariate shift or something. That was the phrase which, yeah, I don't even know what that even means, but anyways, does anyone know what that means? There was like a video for that as well. Yeah, does anyone know what that means? Or yes.
What do you mean by making training more stable?
So layer norms, my view of layer norms is if you don't do layer norms, if you keep, okay, let's say you take a number, 2, you multiply by 2, you get 4. Remember there's 32 layers, right? If you multiply by 2 continuously, you will get infinities in the end, right? Because you like go out of scope of the float 32. So what layer norm does is it makes your number go back to a good scale. So if you do 2 times 2 is 4, let's divide it by 4, go back to 1, right? And so now it's 1 again. If you times 2, it's 2 again. Let's divide it by 2 again, go back to 1. So all layer norm does is it makes a scale go back to a good scale. Like it doesn't, your numbers don't like diverge on both sides. That's what layer norm kind of does. Does that kind of, okay. Any other questions? Okay. So remember the decoder style. Oh wait, I think we actually kind of finished reviewing the Llama architecture. There's nothing else to do. The decoder, right? You do this 32 times. Remember, like for decoder layer is in self.layers. You do this 32. I think it was 32. I can't remember. Multiple times. That's the decoder. You apply this multiple times. You do a layer norm. And finally, you get your logits. Where is it? Your LM head, right? This outputs the probabilities of which token. Remember, we're trying to predict the next token. We output probabilities for each token. And that is called the LM head. And where's the forward function? The forward, right? There's a forward. Right, always with the forward. You go through the model, and then you do, okay, remember, ignore this, right? Ignore this. And you just do the LM head. That's just one line, okay? One line, and then you do the float. Now, another question people have is like, why do you have to do the float? Does anyone know why? You have to upcast a float. Why? Any clues? Have a guess. I probably make this bigger. Have a guess, have a guess, have a guess. Why do we have to upcast a float? Sorry, gradients? Okay, close. Why? Why gradients? It is related somehow to gradients. Anyone have a guess? Okay, it's for training stability purposes. So the softmax, you should always upcast the float 32 because it makes training more stable. If you take the derivatives and the gradients, if you do not do float 32, you might get nans as well. Remember, the exponential can be very large. So you want to take the float 32, which has larger precision than float 16. Right? Float 16 is the maximum number is 65536, I think. I think it's 65536, right? But float 32, the maximum is like some large number to the power of 38 or something, 10 to the power of 38. So that's why you have to upcast it to float 32. This just makes training more stable, right? So all of these things that we do tricks, it's just to make training stable. Yes?
You said you're doing the operation 32 times. Is that just like an arbitrary thing that people figured out works, or is there a reason for that?
Oh, that's up to you. So like if you want to do more parameters, you can do 300 times, up to you. That's just make your model 10 times larger. So like when you hear like, llamas, yeah.
Each time you do it, it's generating like a weight for the model? Is that each layer, like each time you iterate, it's going to generate like a set of weights? Is that what it is? Or is it
So the weights you train, when you take the tokens, you go through the architecture, and like it changes the tokens. And these tokens keep shifting to like some sort of like new direction, and you keep doing this.
So, but if you do it more times, you said you get a larger model from that?
The problem is you have to train more weights.
Oh,
So each 32 times has different weights.
Got it, right, okay. So each iteration has its own.
Correct. Each of the iteration. But it's not, yeah, there'll be 32 different weights for each layer.
Got it, okay.
And so like, yeah, normally people just, if you see like this, like, GPT-4, what is it, like one something trillion tokens? I'm assuming there's more layers, larger embedding dimension, larger this, larger that, more layers. Normally speaking, the more layers you do, the model can learn more. So that's the whole reason why you wanted to add more layers. You just want to increase the capacity of the model to learn. Again, is to make training more stable, again. And so this, remember the shifting trick that we did? In Pytorch, the shifting trick is just this and this. That's the shifting trick. That's the thing that makes it learn to predict the next token. And then you pass it through the loss function, the cross-entropy loss, which we discussed about. And then that's the Llama architecture, and that's normal. The rest is not useful. The rest is, yeah. So in theory, you could write the entire Llama architecture in like, I think 50 lines or something. The rest is just unnecessary bloat, right? All of this is 1,600 lines of comments and stuff like that. But this is for Hugging Face's implementation. It's highly respected. And this is what you should look at first when you read a new architecture. So we just kind of went through the Llama architecture. Hopefully you can kind of get a sense of it. Obviously, if this is your first time reading the source code, it's actually not that hard. It's not that complicated. You just have to see which components you can ignore, right? It's not that scary. Yep, does that kind of get it? Or do you guys kind of get that feel? We're going to do more. Obviously, this is the first one. Any questions? Yeah.
Is there a major architectural difference between Llama 2 and Llama 3?
No, not really. Other than more tokens. I think they changed embedding. They did change some of the numbers, like how many numbers you want to represent for each number. They changed that. large vocabulary. They did much larger vocabulary and more tokens. Other than that, no, there's no change at all. Yeah, yes.
It looked like a lot of kernel you were writing was in Triton. Do you find like any reason to ever drop into CUDA? Or is like Triton pretty much like always?
The reason why, it's funny, I used to work at NVIDIA. Why shouldn't I be writing CUDA, right? The reason is I see CUDA as extremely annoying to write. And if you want to optimize for just NVIDIA hardware, okay, go ahead, you can do CUDA. But my view is like, I don't think so that's going to be forever. So as like a safety precaution, let's just do Triton, right? Let Triton handle the compiling down to CUDA or AMD or whatever, Intel or whatever, right? And Triton can be the intermediary. If you want to get like 10% faster, yes, you should do CUDA. But it's only 10%, right? If you do fine tuning 2 times faster, it's already nearly at the ceiling. You can only go so much. And so like, if you want to go down the extra mile, yes, more than happy to welcome you to do that. But I do not, it's funny because I used to do CUDA all the time, but I don't suggest it. You will get more performance though, but I don't suggest it. Yes, question.
So you never had to drop down to CUDA, right?
Oh, sorry, yes, what?
You never had to drop down to CUDA. You could live with Triton.
Yes, you don't, yeah. So Triton, you write it in Triton, then it compiles down to CUDA. Yeah, sorry, wait, yeah.
Yeah, there's a follow-up on that. Why doesn't Unsloth work on AMD or the other targets?
Actually, it could work. The only problem why it doesn't work on AMD is Triton. Oh, I think. And Xformers. Actually, if Triton works on AMD, we work. If Xformers, so Facebook's flash attention library, if that works on AMD, then we work. Oh, funny, we work. But anyways, it depends on those conditions. So if AMD has those to work, then yes. In theory, you can remove Xformers and just use scale.product attention. So there's only one dependency, which is Triton. I think some people have gotten it to work. So it depends, yes.
I kind of have an answer to that. I've trained on a MI300X instinct with one card with Triton, and it worked with AMD. So
Okay, I mean, if Triton works, then yes.
it just works. So I just have an answer. Sorry.
Okay, no, good, you answered, yeah, okay. Yeah, but we don't, so officially we do not support AMD, but I guess it works. Okay, that's interesting. Yes, okay. What's next? Where's it Gemma one? Yes, okay, so we're now talking about Gemma bugs, specifically Gemma. So if you go to our blog post, we wrote a blog post about all the issues that we found in Gemma. For example, you must add a BOS token. There is a typo in the paper. Yes, so we don't just find bugs and we have to read the paper first to understand the model. Now the problem is sometimes when people release models, they don't release papers. That is very painful. That happens a lot now. So please, model creators, please provide papers. Otherwise it gets more complicated. There's also like some other issues. And we have a Colab notebook which provides all these. So if you open up the link, Gemma details, remember, if you don't have access to these slides, it is tinyurl.com/unsloth, right? That's the slides. If you open up the Colab notebook, this is actually runnable in Colab. Please log into your Google account for this to actually work. But we show that this is the log L2 norm. So we check so this layer number, right? There's like 18 layers. We check every single layer, the output of the actual good implementation, so the DeepMind implementation, with the Hugging Face one, with the Pytorch one, with the other ones. And if you do the L2 norm, you find that the error is very high. And what we showed is that you can actually move the error down by doing multiple changes, right? So each line, you can see there's like multiple lines. Each line is actually a method that we apply to make it better, right? So like we finally found that approximately either the blue line, I mean, it depends on which you like, either the blue line or the black line makes training much better. Does anyone notice any interesting things about this graph? Anything interesting? Like, do you see so remember each line is a fix that we did, right? So like there's many lines and we did a fix and it changes the error. And we selected the black line to be the final one. Does anyone have what is like anything interesting? Yes. So one of them caused a huge jump, and that is a float32 fix that we did for all architectures. Yes. And the other ones are less prominent. But anything else? Anything else interesting? Yes.
Yeah, so the dash line, finally goes up in the letter half, like why?
Yes. Fantastic. Why? I do not know. And that is a good question, and I don't actually know. I think it's just language. I have a theory. The theory is, yeah, but unfortunately, I can't say everything. Like, I mean, my theory is, and there is also a jump as well in the middle, and the blue line, it starts from very low, it goes up very high, and everything does this, right? So like, there is just some weird transition boundary in the Gemma model, right? And so like, I'm just gonna guess. My guess is that when you train a transformer, the later layers get harder and harder to train, right? The earlier layers actually get very easy to train. And so this transition boundary is when the model probably was not really trained that well. So I'm going to guess, this is just guessing, that maybe the model should have been trained for more data, and the boundary should disappear. This is just my guess. So there is a phenomenon, essentially, is like more data, the model, the last layers are much harder to train. And that's kind of my theory, but I don't think so that's correct, but okay.
And the blue one kind of drops for a moment, right?
Yes.
Right before the last one.
Yeah, exactly. So in the end, so now the question is like, why did we choose the black one then? Why didn't we choose the blue line? So that's adding the exact GELU that we found. So if you add the root fix plus the exact GELU, you get the blue line. But we, in the end, decided to do the black line. And why do you think that is? We did not choose the blue line. We should have chosen the blue line, right? But with all the fixes that we did, so essentially, the answer why we did not choose the blue line should actually have lower error, right? The reason why we didn't choose that is because there was not just one error, there were two errors, there was many errors, and all of the errors compounded together, we finally chose the black line because it matches the original implementation. So, because remember, the trick is you have to match the original implementation of whatever the Gemma model creators did. So you can't like just look for this error. Maybe like, maybe like if someone chose different like fixes that we did, you can probably get even a lower training loss. I guess you could. But we decided to choose the black line because that's what the original implementation did. Any other questions?
For my own clarity here, so I know the weights they're trained, and when you kept saying the model could have been trained, you're not talking about the weights, were you?
Oh, I'm talking about the weights. Okay. So the weights are the ones so the model weights are the ones training, right? So the rest you don't actually train, it's just the weights itself.
Yeah, because it's a bit meta, right? Like at the end you end up with a model that's the transformer, and the weights themselves have to be trained. So anyway, that leads me to my follow-up question, which is, do you have examples of that weight training? I guess, what are those training based off of? Is it iterative where you're just going to see the training loss over time, and you're just trying to find the right weights that give you the least amount of loss?
Yes. So remember the goal of a transformer is you want to predict the next word, right? So the sentence, hello, my name is Daniel, you're trying to predict hello, predict my, right? My, predict name, and so on. You have this data, correct? Like just take novels, you shove in the novels, you essentially created data out of thin air. And then you change these weights using like backpropagation, do derivatives, and try to like change these weights such that you get the highest accuracy. And this training procedure is called backpropagation. And so like, I was trying to show you like how do we actually derive the derivatives. When you do backpropagation, you need to derive the derivatives. Just use Pytorch. Pytorch will do the derivatives for you. And yes, but does that kind of answer your question or?
Yeah, I think that gives me a glimpse of some of that stuff. Yeah.
Okay, yes.
So you mentioned the middle layers later layers are usually undertrained.
Yes.
And often for fine-tuning, you see that the first layers get overtrained. I know that people are doing layer freezing now, but is there a way to change the learning rate dynamically based on the layer?
Yes, the Unsloth actually has that. So you can actually, depending on your layer, so for now, what we do is your embedding and your final layer, you can change different weights, different learning rates. So we found that if you train the last layer with the embedding weights and the embedding weights in the LM head by a factor of 10 smaller, the learning rate, you can actually have increased accuracy. So yes, you should. You should change the learning rates for each layer. But people don't actually do that. I think it's because if you set a learning rate for each layer beforehand, you're kind of like, it's like you're like doing subjective bias. So like that's why people just set one learning rate for all the layers. But I think in this case, I'm just going to guess. Okay, this might be a transformer. This is transformer general. This is not just for Gemma. This is for all transformers. Maybe, I guess, layer-wise learning rate could work. I think there are like some papers which do that. I think it's called Lars. I think Lars does layer-wise. I think it's called Lars. Layer-wise learning rate. If hopefully that answers your question. Yes. Oh, it's a log L2 norm. So you take the DeepMind implementation, you code it up correctly, then you take the other implementations like PyTorch, Hugging Face, even DeepMind's own implementations, and then you check each layer, the output, you compare it with the original, the correct implementation, and check what's the error. And that's the thing that I graphed. And your goal is you want the error to go to 0, right? So like you want it to go all the way to 0, so like on the bottom, and not like very high. And that's log scale, right? So the error is not like a small number, it's 1,000, right? So like every single line, every single step you go down is a log difference, right? It's not like I essentially logged it. If you did not log it, it would look very bad. But I just logged it. Yeah, does that? Okay. Any other question? Yeah.
So let's say if there's an issue in a tokenization part,
Uh-oh.
a fundamental thing, or we find some optimization or a bug, and you have to change the way you're tokenizing your sentences and everything, would you have to retrain your models to like incorporate these fixes and changes to the tokenizer?
This actually happens a lot, very frequently. And I think for example, Tiny Llama, someone tried Tiny Llama and then training already 80% completed, they found a bug for tokenization. They're like, so it happens very frequently and it depends on what you want to do. I think it depends to the model creator. If you already spent millions of dollars, maybe just train it with the bug and then you release the bugged version. But it should still work, hopefully. Yeah.
So in theory, let's say if OpenAI would have a lot of difficulty shifting if they found, like if somebody else found an more optimized tokenizer or something like that, they would have trouble shifting to that model because they would have to spend like...
You have to retrain everything, correct. So you just assume it, just leave it. If you already spent like billions of dollars, probably not a good idea to retrain.
So even if it offers like 2x optimization or somehow, like they would have to spend, like they would have to retrain and spend...
Yes, you have to retrain everything from scratch. But that's why I think that's why you should do like small scale experiments. Get like a smaller model, train it for less data, test it, and then see if the accuracy is good, and then you scale it up. Yeah, any other questions? Okay. I will, yes. So there's a notebook. So we show step by step exactly what we did. And if you inspect the code, okay, the Gemma code is now, the Gemma code, wait, no, it's modeling Gemma. Oh, okay, maybe I should just go to Hugging Face itself. Wait, let me go to, you can actually find this. If you copy paste this, right, you edit you go to Gemma, and you go to modeling Gemma. Right, this is, oh, did I not? Okay, let me just, okay, maybe I typed it wrong. Did they not? Oh, okay, maybe I did 2 L's, my bad. I always get confused on that. Oh, what is this? This is interesting. Okay, this is like new. So, okay, yeah, I did not, yeah. So all of this, so we wrote inside the, Llama does, so we showed, for example, in the code now, if you go to like Hugging Face's code for Gemma, I tried to write some comments, for it to be more clear why we are doing this. And so for example, the layer norm, right, you have to be careful to where you upcast and downcast. And we write this in here. Where is it? I think it's, no, not, oh wait, is it? No, I'm pretty sure I wrote it somewhere. No, it is here. Yes. Okay, it's a bit unclear. I need to make this bigger. Okay, it's a bit blurry. But you can see that depending on the model, in Gemma, you have to actually upcast to float 32 everywhere. You must use float 32 everywhere because the original implementation used float 32, right? So you must always follow the original implementation. If you don't follow the original implementation, then you will get wrong, like, somewhat worse results. And the problem was other implementations just copied Llama and Mistral's code, and they did not do this. And so we found that you actually have to upcast correctly over here, right? You have to upcast immediately. And then you downcast at the very end. And so we wrote a few comments, right? Llama does x.to float 16, whilst Gemma is x, it really, Llama does that, right? But Gemma does this, right? So there are small little issues, downcasting, upcasting. Another question is why do we have to do downcasting? Does anyone know why? Why is there always downcasting, upcasting? Float 32, float 16, float 8. Does anyone know why we have to do downcasting, upcasting? Yes, correct. It's for faster speed. So do you know how much faster? So float 32 to float 16. What do you think? It depends. Who said 2? Okay, good guess. Why did you guess 2? Well, that's for sparsity. Okay, yes, okay. Float 8, approximately 2. Actually, it could be more. So float 32 to float 16 is actually not 2. It's actually much more. I think it's 5, I think. Or is it 6? The reason is because the representation of the float is different, right? So float 32, I have floating point representation Wikipedia. I think it's in here somewhere. And maybe I go to beat float 16. Where is beat float 16? Brain float. B float? Beat float. Yes. Right, so there it is. Oh, there's more pictures now. Oh, they edited this. I did not, okay. This is new. I didn't see AMD FP24 format or Pixar. Oh, okay. They have weird formats now. This is float 32, right? And float 32, the exponent has 8 numbers, right? The 8 bits, and the fraction of a bit has 23. And when you do matrix multiplication, does anyone know how to calculate the number of transistors you need for float 32? Does anyone know? It's a formula that's related to the exponent, the fraction, and just the exponent and fraction. What do you think the formula is? Have a guess. Right? I said that it's approximately, so if you have B float 16, the fraction is 7, right? B float 16 has 16 bits you can use. The exponent is used for the dynamic range of the number, right? So if you want larger numbers, you have to have larger exponents, right? So this means B float 16 only has a range of 2 to the power, okay, it's not 2 to the 8, but just assume, it's 2 to the power of 8. Okay, that's not right, but just assume that. 2 to the power of 8, right? But, yeah. And this one, float 32, also has 2 to the power of 8. There's another format called float 16, which is 2 to the power of 5. And then the fractional component is 10. So all of these numbers you can scale, right? How many do you want for the exponent? How many do you want for the fraction? You must include the sign bit. And the trick is you must have 16. You need to fit, 16. So you could have exponent 1, and fraction could be 14. That could also work. But does anyone know how many transistors you need to use for float 16, for example? And B float 16? Remember I said it's around 5 times faster. It's actually not right. I think it's even more. What is the formula? Have a guess. How many transistors do you need to use to do float 16 multiplication, approximately? Or float multiplication. It's a formula related to exponent and fraction. The answer is exponent plus fraction squared. That's the answer. So what does that mean? That means float 16 is 5 plus 10 squared, right? And float 32 is 8 plus 23 squared. So it is not 2 times faster. It is much faster, right? So I don't know what that is. What is, so it's 8 plus 23 squared, 500 so you need approximately, okay, this is approximately, you need 537 transistors for float 32 multiplication. Oh, it's just 23 squared. So it's 8 plus 23 squared. Yeah. And so what is the other one? I think it was, what's that? I can't remember. So it's 8 and 7, right? So 8 and 7. This is Google's format. It is 57. So what does that mean? How many times faster? Yeah, so it's actually 10 times faster, right? So float 32 to float 16, B float 16 is around 10 times faster, right? Float 16 is 5 plus 10, right? So 5 plus 10. So B float 16 is approximately 2 times faster than float 16, although to tell the truth, no one really notices any difference. But in general, B float 16 is actually faster, right? So that's why it's not 2 times faster, it's 10 times faster. And that's why you must use Tesla T4s, as I said, because it has tensor cores, which does this, right? The tensor cores does float 16 multiplication very effectively and very efficiently. And so do not use P100s again, right? P100s do not have this methodology. Yes, question?
Why don't we go even smaller than 16?
Yes, float 8. So float 8, I don't know. There are 2 formats for float 8. Oh wait, I don't think so. It's in Wikipedia. Float 8. Oh, okay. Floating point. It's called EM. Oh, I'll just use mini float. Does it? They have some. Yeah, there we go. Right. So you get to decide. Remember, if you want to have 8 bits, you get to decide how many you want to do for the exponent, how many you want to do for the fraction or the mantissa part, right? You get to decide, and depending on the company, you know, it's unclear. There's no standard. So this one's 143, right? So like, what's 143? 1 plus 4, right? 4, 3 squared, right? Is that 4, 3? Yeah, 13. So float 8 is, I think it's around, yeah, so around 4 times faster than B float 16. But in general, it's not. Okay, in general, it's like 2 to 3. It's not going to be 4. The reason is because you're packing so many transistors in. You also have to do like energy. You have to like do the data movement. There's like other transistors you have to do. approximately, it's 2 to 3 times faster. That's float 8. Can you go even lower?
Yes. Why don't we go 1?
1 bit? So you must have the sign though. So you can't do 1 bit. So 1.58 bit, some people have been talking about. 2 bit. 2 bit could be possible. The problem with 2 bit is it's problematic because when you do 2 bit training, yes, okay, so let's see, let's do 2 bit, right? So what do you want to do? How many exponent? 0? And remember, you have to have a sign bit. That's the most important. 1 for the exponent and fraction 0, right? That's because remember it's squared, so plus 1. Oh, wait, no, it's 0 plus 1. Okay, so it's 1? Okay. 10 times faster? I don't think so. Okay, maybe 2 bit is probably too low. Maybe 4 bit. 4 bit could work. Yeah, yes?
I have a question because, how does this map to the flops on, say, NVIDIA's spec sheet? Because I understand it's math, but they, for example, have the same tensor flops for DF16 and FP16. They don't do it.
Oh, that's just because they wanted to do that. Just for easier calculation. Like,
And then for their tensor 32, they do list the 2x, so that's why I would guess.
tensor 32 is not 32. It is, they have it somewhere. NVIDIA. TensorFloat, it's 19. That's the trick. They like to do marketing. They say it's 32, but it's actually 19. Yes, that's why it's the same. Okay, any other question? Was it someone else raise their hand? Or okay, but yes, I was going to say you can do 4-bit, right? So 4-bit is actually a NVIDIA's new GPUs. The B100s do have 4-bit. So that is approximately 2 times faster. Now the reason it's not, okay, let me just try 4-bit. I think it's 1 plus, it's probably like 2 plus 2 or something. I don't know, 6. Okay, right. It's not going to be that much faster because, as I said, there's power transistors and there's other transistors. You can only go so far. Just the jump from float 32 to float 16 was very large. Yes.
So, quick question. So, for the example, the 1-bit bitnet, that
1.58 bit, yeah.
yeah, so that would be an example of 1-bit, like in this.
So it's a different. So actually, I had a tweet about this. 1.58 bit and float 4 is the same in terms of number of transistors. You'd rather use float 4. Okay. The reason why is 1.58 bit is you have to do more manipulation to make it work. You have to use the straight through estimator. It's a horrible mess. You'd rather just use float 4. So float 4 and 1.58 bit are similar.
You get to create your own base model if you do if you replicate the paper.
Yes. What do you mean?
Which most of us have never done, right?
Mm-hmm.
Which would be.
Technium and the Noah's research probably replicated there some, though. It does work, somewhat. Somewhat works.
I mean, yeah, it's 1 bit, but I mean.
1.58, yeah. It's not actually 1 bit, yeah. It's like, I think it's like 3, yeah. Oh, yeah, they like to call it 1 bit,
So,
yeah.
but my question is like, so in theory, like, obviously, I don't know who works here, but like, most of us have never built a base model. Right?
Yes.
So, like,
Well, you could, yeah.
Yeah, you can with enough GPU power, but 1 bit, that, you know, that was, and they even had like a really great tutorial and like, so, but do you think that that's just like, I'm just asking for your opinion on that.
I don't think so. 1.58 bit will be the future. I think NVIDIA is like the focus is on float 4. They might go to float. I think float 4 might be the final precision. I don't think you can go any faster with that. I think float 4 is the final, no more. So we won't be having that much faster GPUs. I don't think so. I mean, float 4 is actually, they don't actually do float 4 anymore. It's actually float 6 for the gradients, float 6, and then float 4 for the activations. Like, you know, it's very weird. I mean, you could do like float 3, float 2, but like it's your diminishing returns.
So, in ARM silicon though, there's been like advances in like super low bits versus
fixed point stuff?
Huh?
Is it called fixed point stuff? Or
Huh?
I think it's called fixed. I knew ARM has fixed point.
Oh well, yeah. So it's I mean, just like the Snapdragon X, like the new.
Yes, they have. So it's like customizable as well, or I don't know.
Yeah, well, okay, so the SDK is broken. You have to pass the, so this is why you can technically run Mixtral 8x 7B on your phone at like 20-something TPS, is because you can use UFS 4.0 as flash storage and subsequently use that as memory, and then but the thing is, then you're running at 2-bit precision, which is
so that's probably why this, so if you use 2-bit precision, that's why you have memory reductions. But there is actually papers which show that if you do 2 bits for the MLP plus 4 bits for attention, that's actually the most appropriate. You can actually do that.
So that's not a invalid approach.
No, that's not invalid. That actually, it works. It works. The
I've seen it work.
Mobius people did that, I think. Yeah.
That's all.
Yes, question. Sorry. Okay.
Two kind of related questions on precision. First one is like, why is the negative bit, like, you must have the negative
The sign bit?
Yeah.
You don't have to, but it's generally like standard practice to have the sign bit. In theory, you don't have to. The only problem is if you don't have a sign bit, your numbers will be 0, 1, 2, right? But then what happens if you wanted to like make the model, like you're trying to not make the model learn negative directions anymore? You could do that. I don't know if there are papers. Maybe you should write a paper about that. Train a model on that, and let's see what. Okay, but yeah.
Well, in very related, I think, because it's all bits, it's all bits, right?
Yeah.
Softmax, you're basically just linearly like fitting stuff down to a certain number of bits. There's nothing special about softmax and things that could be like exponentially big, sort of going this way, right? Like
The reason.
find this to be better.
It's because remember, when you do softmax, you also have to normalize by the sum of the exponentials. And if you do exponential of 10, you already get like some large number, and this probability will take over the entire sum.
Well, but you're not like blocking it. You're just square rooting it.
No, it's the sum of exponentials divided by, the exponential divided by the sum of the exponentials.
Yeah, but like the biggest exponential dominates the sum, right?
Yes, that's the problem though. If you do that, then your model's not learning. You're just trying to learn to predict one token. Why don't you just predict that one token then? Like the largest one that you did. That's kind of what you're forcing the model to not learn anything. That is why you have to like minus the maximum. That's a trick that we showed. Is like minus the maximum, and then you can like reduce this effect of this one token, or this one issue. So it's for training stability purposes. I don't know if that kind of, okay, probably that didn't answer your question, but okay, yes.
From a practical perspective, how much slower was upcasting the layer norm, and then do we know whether that's actually more accurate than the way that Llama does?
That is a good question. To be honest, I do not know. I don't think so. It changes too much. Layer norms, if you upcast, it's probably, yeah, small effect. But the reason why you need to upcast is because Gemma did it before, so you have to do it. Remember, the trick is you must follow what the original implementation does. Any other questions? Or okay. There are like some other issues which we showed that more, okay, it's funny because it's all about upcasting, downcasting, and stuff like that. Each implementation does its own thing. Unfortunately, how do you actually analyze this? You have to open 3 screens up. The DeepMind one, the DeepMind one. Okay, okay, I'm too excited. You have to open up 3 implementations, the DeepMind one, the Hugging Face one, the Keras one. You have to open 3 screens and you see line by line, what did they do? And then now you have to guess which one's the correct one. The guessing part is the most painful. So you have to like inquire. You ask Hugging Face, which one's the correct one? You look at the paper, which one's the correct one? You assume the DeepMind one's correct and stuff like that. So there's like some human component you have to guess. Guessing. So that's probably why it can't be automated, right? These error checking things cannot be automated. It's because there's a human there which made these decisions. And so now you have to decide which of those decisions did they choose. And you can't really automate this away. I guess you could automate this by doing the methodology which we described. Try all combinations and see which one has a lower error. I guess you could do that. But remember, you must have the original implementation first. That is a problem. So there's like chicken and egg problems. The rope position. So this is the one I was talking about, upcasting rope. This is in all architectures now. You must not downcast rope. If you do, you'll get wrong results. So previously on the left, right, if you see 8192, 8192, 8192, that's the positions. That is definitely incorrect, right? What does that mean? Like, do you know why that's incorrect? 8192, 8192, 8192. Does anyone know why? Remember, this is positions. Why is it all the same? Like, does anyone know why this is really bad? So we kind of like, essentially now the 3 words have the same position, right? 8192 is the position. And what is another big error of this? There's actually one more error. Let's assume the maximum is 8192, the sequence length. What is 8192? It's out of bounds. Remember, it's -1 for Python, right? It's 8191 is the correct number, right? So if you correct this, you get 8189, 8190, and 8191, right? And you can see all the numbers are like this. So the point is if you remember, the whole point of this problem is because we're using float 16 for faster training. Remember, float 16 is how much times faster? Yes, around 10 or 5 to 10, something around there, right? That is why you have to do this. And these are the issues prop out because of this issue, right? We're trying to make training faster, but then these issues come. And the GELU one, which we described before, this was the first bug that we found. Actually, I think this is the main reason why we were trying to look through bugs, is we found that, oh look, there is this bug in GELU in the activation function. And so the point is Keras used approximate GELU. The Pytorch version used exact GELU, and Hugging Face also used exact GELU. And the question is, which one is the correct one? Is the exact GELU correct? Is the approximate GELU correct? So what's the difference between exact and GELU, GELU activation function? Where is the, I don't know if they have the exact and the, that's called flax. Oh, okay, that's night mode. Oh, that's even worse. Okay, whatever. Oh wait, that's prelude. Where is GELU? Oh wait, no, I have to find it right. Yes, right, so like the exact GELU is this one, right? There's an error function. Okay, my thing is not rendering it properly. But essentially what you do is you use Desmos. So what I like to do is I use Desmos, right, and literally plot them together, plot them on the graph, right? So like if you have, right, x, y is equal to x over 2, right? You literally type this in. And what is this? I think you can do error function. Oh yes, you can. Right, you can do error function, right, x divided by square root of 2. All right, that's the exact GELU. Right, now you type in this complicated formula for x divided by 2, 1 plus than what? I don't remember this. Square root of 2 divided by what? Was it pi? Oh, it's pi. Pi, and then what? X plus 0. can I, oh, we can't, okay, 0447, 0447, what was the, oh, 15x to the cubed, was it cubed? Yeah, okay, right? Oh, is it? Oh, you're right, okay. Wait, is that, oh, is it just the rendering problem? Or is it square root? No, it's square root of 2 over pi, I think. Wait, is it correct? Wait, I did something wrong. Maybe I did something wrong. Oh, whatever, who cares? Just assume, okay. Oh, wait, oh, you're right, I put the square root everywhere. Oh, is that what you were saying? Yeah. Oh, okay. Oh, no. Whoops. No, get rid of that. Okay, let me just, no, it's tan of everything. Now I have to do this. Oh, yeah, this probably have to play around with this. Oh, there we go. Right. So the blue line, if you remove it, the blue line and the red line, right? They're the same thing. But what's the difference? Remember in Desmos, I don't know if people know this, but you can actually do derivatives. D over dx. Did anyone know this? You can actually do derivatives. You get your d over dx. And then you can do this as well. D over dx. Right? And they generally align. Right? The exact GELU and the approximate GELU generally align. And guess what? You can also do integration. Integral of minus infinity. Oh, did I spell it wrong? Oh, infinity to infinity, right? Of, I think this works. I'm not 100% sure, right? You take your exact GELU, you minus the difference. Oh, I don't think so. This works. Yeah, I don't think so. Oh, yes, it works. Yes, it works. So what you do is you can take the integral of minus infinity to infinity. So the entire line, you minus exact GELU and the approximate GELU, and you do dx, and there is a difference, right? But the difference is very small, right? It's like 10 to the minus 16. It's very, very small. And notice it's like when we do fast Triton kernels, I generally use this feature. So you can do integration and derivatives, and you can use Desmos. So I highly recommend Desmos. And if you do this, that's where we found the problem. It's like, oh, okay, there is some sort of issue. And if you fix it, remember, the GELU fix does do some effect. It does do some effect. But remember, we only showed there was only very small effect, so it's not that useful. The rope fix was the most important, right? The rope fix actually caused issues. So you must fix that. And that's the most important fix that you must do. And finally, there is like some other things that we do. Depending on the precision that you use, there is actually a difference between float 16 and bleed float 16. And if you do this, we show that float 32, remember we showed before that in the fixes that we did, the lines sometimes go back up, right? But actually, if you do float 32, it actually does work. If you do float 32 precision, the lines actually do separate very well. But once you use float 16, the lines then match up again, right? And bleed float 16, the lines match up again, right? So this is just a phenomenon that you're using fast, smaller precisions, and that is why you have this problem. But if you do use full precision, you get good results. And the fine-tuning notebook for the Gemma one also works. So Gemma is 2 times faster and uses like, I think 60% less memory as well. It's more now. So if you run this, remember you have to connect to your Google account and you will get this to run. Any questions on the Gemma one? Okay. Yes.
Sorry, I came in a little late. Could you just summarize the graph you just showed and
Okay.
lines over number of layers?
Yes. Where did I put the picture? Oh, wait, it's in the blog post. Yes, that's fine. Wait, where did I put it? Oh, it's the first picture, right? Yeah. This one, right? So the x-axis is the layer number. So Gemma has 18 layers. So each of those, the x-axis just indicates which layer it is. The y-axis is log to norm, log L2 norm. So what you do is you take the original implementation, like DeepMind's implementation. You take Hugging Face, Pytorch, the other implementations. You check the output of both of them. So the output, you run the model through. You take output to layer 1 and output to layer 1, your other implementations, and you just find the error. And so this is just the error. And this is log scale. So when it's log scale, it looks better. When it's not log scale, it looks very bad. So is that better?
So this, you're taking the output of each layer.
Yes, output of each layer. Yes. that's called Gemma. So that's for Gemma. For Phi-3, similar. What you do is you open up the Phi-3 implementation, you read through the Phi-3 implementation, and because like you guys like most likely can go through Llama and like just look at it in general, remember delete useless parts of the code, you will see there are differences in Phi-3. And the differences are they use other methodologies. They use upcasting, they use stuff, but there was a weird thing that we found in the config file. I will show you. Phi-3 config. Okay, I'll just use the instruct version. If you go to, always when you go to like new models, always read the config file, right? Config.json. When you open it up, it tells you all the tricks you need to know about the model architecture. And I highly, right, it tells you what is the EOS token ID, 32,000. Right, when you look at this, is that a good idea? 32,000, 32,000. What is the EOS token ID? Right, 32,000, okay, that's fine. The pad token, no. Is that a good idea? Like you have to think about like why are they there? How many layers does Phi-3 have? It's 40, right? So 40 layers. How many positional encodings does it have? So how long, what is the context length? It is 131,072. That's the context length. Remember, it's 100. So this model, the Phi-3 medium is 128K, right? It's not 128,000, right? Just be careful. It's actually 128K, right? It's 131,072. There are other issues with this model as well. Okay, this is okay. That's probably okay. Probably don't use the instruct version. The instruct. We choose the small version. This is a smaller version. There is a thing we noticed is a sliding window. So Mistral has sliding window. Sliding window essentially attends to only 2048 tokens. And this just makes training much faster. And does anyone notice what the problem is for this? Why is it 2047? Anyone notice any issues? Yes?
Well, it's not a power of 2, but... I mean,
correct. So is that weird?
I mean, that's horrible, yeah.
So I did ask the Hugging Face people and they said, yes, it is a bug. So they actually did fix it. But then I don't know why they reverted it back, so I'm a bit confused. They kind of forgot about this. Yeah, so it's supposed to be 2048.
Yeah, because that only makes sense, because you're training on 4K, like, you know, you're training on the correct context, right? Then this sliding window makes no sense. In fact, I've seen a lot of sliding window bugs recently.
Yeah,
so like, for some reason.
Yeah, I'm not sure why. But I'm pretty sure this should be 2048.
Yeah, I'm very confident it's sorry.
I'm 100% sure it should be 2048. Yeah, it's not. Yeah, and yeah. So these small issues they need to fix. They still have not fixed. But in Unsloth it's fixed. So we actually uploaded models which fixed them. Right. So if you go to our Unsloth Hugging Face repo, we actually have models which we fixed all of them. Oh, this is too big. Where is the Phi one? Oh, I didn't put it up. Okay, I need to find the Phi one now. Where's Phi? Oh, there. Phi-3 mini 4K instruct. Right. If you go to files, you go to config.json, we fixed it. And there's other things that we did to fix it. For example, the pad token ID is 30. Okay, that's actually wrong. Okay, okay, I need to fix my own. Okay, anyways, there is a bug which we discovered ourselves. It should be 30. This is actually wrong. Another thing is you must not make the pad token the same token ID as EOS. Never, 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 never. This must be a different token to the EOS token. I do know Unsloth, we automatically fix this during the loading. It's just the config itself is not right. But that's okay. Unsloth itself is fine. Just the config is a bit wrong. Oh, okay, I found my own bugs, but okay. Yes.
Okay, never mind.
Oh, yeah.
I'm not going to slow down you keep going, because there's a lot of slides.
Okay, yeah. Actually, there's not that much slides. Okay, actually there is. Oh, okay, I just noticed we have more. Okay. So another one is like Phi-3 used, they merged the Q, K, and K. Remember we did Q, K, and V? They're unmerged, right? The weights are separate for the attention matrices. Phi-3 did a very interesting move, is that they fused them into one matrix. And we found that to be very problematic for fine-tuning, because if you fuse them together, when you do LoRa adapters, you actually only learn new extra weights, and that's very less. So please unfuse them. And we do this, so our version of the Phi-3 actually unfuses the weights. You must unfuse. Actually, I have to highly suggest you to unfuse the weights. you can only fuse them if you want to do training faster. This will make training like maybe 5% faster. It's actually not that much. It's like 2%. You actually increase memory usage a lot. So just be careful of that as well. Oh yes, they actually did. So this is the sliding window one. They actually fixed it. And then they unfixed it. I think they just forgot about it. I'll probably like push them again to fix it. And this is the fusing of the weights. So we show that if you actually unfuse the weights, so Q, K, and V must be separate. You must not combine them. If you combine them, you actually have lower accuracy. So please do not do that. For tokenization, remember this slide which I showed you about the smiley faces are like the spaces and each one's are different tokenizations. There are actually many issues for tokenizations. This is a totally different separate topic from finding bugs and issues in language models. This is a whole topic of its own because tokenizers are very problematic. And they're very hard to find and fix. Did I double this slide? OK, I doubled that. And also, we have new Llama support, which we have not announced yet, which you can try out. So lots of people have asked us for how do we actually fine-tune a language model and export it to Llama effectively. Does people do know what's Llama or no? Or does anyone not know what's Llama? OK, so Llama is like a interface. When you fine-tune a model, you have to run it, right? You have to run the model somewhere. And Llama just makes you run the model much easier. So like, you know ChatGPT? ChatGPT is like the running mechanism. Llama is just like ChatGPT, but they don't have the model. You have to select a model. That's kind of Llama. Yes?
How did you manage to like, so I've been working on converting, creating model files using the automated pipeline, but we've found many issues trying to automate model file creation.
Is this using Unsloth? No? Or is you using Axolotl or something or other ones? Did you automate the model file yourself or?
Well, because we need our own model files, right?
Also, we do this automatically now. So with I spent like 1 month on trying to automate the model file creation.
That's why we were struggling so hard as a company.
Yes, I have code for that somewhere.
If you could, okay, if it's open source, then.
Yeah, it's already in the GitHub repo. So if you go to Unsloth, you go to chat templates. We have code for that, Llama. It is still very ugly. So these are the chat templates for, remember the BOS token. Someone mentioned you have to add it. Yeah, add the BOS token. This is the Llama chat template, so Llama has a specific requirement is you must have a chat template because if you don't use a correct chat template, your model will output incorrect, like substandard responses. So this is the chat template for like some of them. We had to write chat templates for all of the architectures, and we have an automatic one. So these are Vicuna and blah, 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 alpaca style, Gemma, the Gemma style, we also have that. We have many, even the Llama 3 chat template we have as well. Now for the automatic one, so what we do is we can actually make an automatic chat template, a model file for you automatically. And this makes your fine tune much more accurately. Wait, I'll show you where is the code for that? Where is the code? Okay, you can see the code is quite large for just the chat templates, right? This is just for tokenization. So it's not even yes.
This is Apache 2.0, right?
Yes, it's Apache, yes, it's open source, yeah. Wait, where is it? Okay, so we have something called parse combine prompt, which does some O of n squared. I didn't actually optimize this. It does O of n squared. I should have done O of n, but anyways, it's O of n squared, checking the prompt. Here's the prompt format. So it looks quite ugly, the code for automatic model file creation, but we actually made it so you can actually it automatically creates a model file from your chat template. You can see it's quite ugly, but it works. Yes, oh, it's even more ugly. Yep, it's quite ugly code. But unfortunately, the model file is very hard to create automatically. And so we have the notebook which allows you to do this. So this notebook is in here, Llama for alpaca. So this one's for the alpaca dataset. And so this is our installation, Llama 3. Where is it? So we'll be using the alpaca GPT-4 dataset. So you use the alpaca dataset, and you use GPT-4 to create the dataset. And the trick is, though, we also have a CSV file now, so you can actually upload a CSV file and use Unsloth directly to fine-tune a language model. But the problem is, a language model must have an instruction and output, right? Only 2 columns. CSV files and Excel files can have many columns. So what do? You have to merge the columns into one. So remember, each of those columns in your Excel file, convert them into text. And for example, the Titanic data set, you merge them to say they have one siblings and spouses and so on, right? You merge the row into one row. And that's what you do. And with Unsloth, you can do this now. I still probably need to edit the syntax calling, but this merging technique says, okay, your first column is called an instruction column, and the 2 double brackets means it's optional. So if the input column exists, then it will say the instruction followed by your input is. And you can make this very crazy. You can do as many columns as you like. I don't know if the syntax is useful, but I will probably be editing this. We're going to make a YouTube video about this to talk about this. This is actually very important for fine-tuning. We noticed that every single provider requires you to use only one column for instruction and one output column. Now you can have infinite columns, well, how many you like, but you must define the chat template. And we also have a customizable chat template. So before, when you do fine-tuning of language models, you have to use the alpaca prompt in our other notebooks, right? Below is an instruction that describes the task paired with an input, blah, blah, blah. You put your instruction here, you put your input here, and you put your output here, right? But notice, what is the problem with this? Is there a problem with this? So you must only put one instruction and one output or response, right? The input is the problem, right? So how do you solve this? You solve this by merging the input into your instruction prompt, right? So this actually should be removed entirely, right? And your input should be something else. And what you do is we can do this now, right? So you must put the input and you must put an output, right? You can only use 2 columns now. But you can use, remember, even though you can only use 2 columns, you can use this to convert your data set into 2 columns. Yes?
Do you lose any of the semantic meanings though?
Oh, no, I don't think so. No.
You don't think so?
No, I don't think so. It depends on how you format the data set.
Okay.
Remember, it's a language model, so you can do, the more you tell the language model what to do, the better.
Of course.
Yeah. But the problem is, to do the model file creation, you must do 2 iterations, repetitions of this, right? You must do instruction response, and then you do another one. You must do this for Unsloth. I found this to be very, very important for the model file creation. If you do not do this, you have dangling new lines, and you actually make your model output terrible. So you must do 2 repetitions of this. Okay, it's a must. And if you don't do that, we'll error out. And so once you do this, we also have examples of, for example, this is Llama 3's chat template, right? We, again, do 2 iterations. You must do 2 iterations, most important. And when you finish training the model, remember you can do runtime run all. You can do inference now, right? Continue the Fibonacci sequence. Your input is 1, 1, 2, whatever. And the next number Fibonacci sequence is 13. I think that's correct. Yes, that's correct. So your language model has learned how to do Fibonacci. And because it's a chat template, you can shove in multiple messages into the model. So this becomes a ChatGPT for you. This is a customized ChatGPT that you can use. And finally, when you want to save the model, you can save it to LoRa adapters. So this only is 100 MB in size. So once you fine-tune the model, you have 100 MB. But some people also want to merge the model back, and that will take 16 GB. But you must merge this for Llama support and GGWF and stuff like that. And what we show for Llama support is you first have to install Llama. You select what you want to save the model to GGWF. So this is 8-bit. We now support multiple quantization methods, right? You don't have to do 8-bit. You can do 4-bit, 5-bit, whatever you like. And this will be saved into one go, much faster. In fact, I think this will save you 20 minutes of your time. And we save this automatically. Okay, and this does all the saving, blah, 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 saves. And we also, you see, we automatically create an Llama model file automatically using a chat template. And I can verify this is actually correct because I tried it. And then when you want to serve the model file, you can actually print out the model file which we created. And this is the model file. Whoops, I pressed run already. Anyways, and finally, to serve it, you can just do model file to serve it. And you can serve this. And we do have a CSV version, so you can actually use the Titanic dataset. Okay, it's loading. So if you want to use the Titanic dataset, you can upload the Titanic dataset, right? I upload the Titanic CSV. You can use the CSV file for this. And again, you have the merger columns and so on, right? This is a more complicated example. In fact, I should provide this entire example for you for the entire Titanic dataset to merge all the columns into one. And it's the same exact output. So that's the notebooks that we're sharing for. We did not release this yet, so this is for you guys to like experiment and see if there's any issues. Yeah, and just tell me. We also have blog posts on our website, which you can see, our Unsloth GitHub repo. And we have stickers available, and they're very, very cute for you to take. And yeah, and also, yeah, we have Q&A now. Yeah, yes. Oh.
Did you measure the difference that it makes to write the CSV content in English sentences as opposed to just dump them or put them in JSON format?
The problem is if you put them in JSON format, you still need to have instruction and output. So how would you do that? You need to have 2 columns only for fine-tuning.
Can you do like, in your template here, you have instruction, and then you add all.
You add all of the other columns onto it.
Can you just put the same instruction and then JSON of the values of the columns?
Yes, you could do the JSON file. Yes, you can. But we just show you that you can do multiple columns now. So like if you have like 10 columns, you can now make the 10 columns into one by merging them together. Does that kind of?
There's a big difference in representing that merged columns as an English sentence or like a dictionary.
Oh no, you can't use. You mean like you shove in the actual dictionary for fine tuning? I mean, you could do that. I think you should do English language because a language model predicts the next word. JSON is probably less useful. Always convert it into English.
I have the same intuition. I was wondering if you measured it.
Research paper. Yes, it should be another research paper. Yeah. Any other questions?
So
Yes.
There's a lot of upvoted questions from me on the chat. Sorry, it's.
Oh, there's.
I was wondering if you could take a look at them.
Oh yeah, I didn't actually check the slider questions. Whoopsies. It actually didn't load. So, oh, there's lots of questions. Okay, I will. Okay. Oh, okay. Oh, okay. Oh, okay. I need to answer each of them afterwards. I think I'm already out of time though. So, yes. Thanks a lot.